in-order traversal. So we look at the root node and then we realize that it has a left child. So it has a left subtree. So we do not visit it yet, which means we do not print it or we do not add it to our list yet. Rather, we follow the path on the left side and then we come across 3. And then we realize that, okay, 3 also has a left child. So we don't visit it yet. So then we go down to 1. We go down to 1 and now it does not have a left child or a right child. So we can visit 1. Then we go to 3. And now we visited the left subtree of 3. So now we can visit 3. And then the next step is to visit the right subtree of 3. But of course, 3 does not have a right child. So there is no right subtree to visit. So we can move back up to 2. So now we've visited the left subtree of 2. So now we can visit 2. So we print 1, 3, 2. And now once we've visited 2, we can now visit the right subtree of 2. So to visit the right subtree, we go to 5. Once again, we realize that 5 has a left subtree. So we go to 3. Now 3 doesn't have a left subtree. So we can visit 3. Then we visit 4. Then now since we visited the left subtree of 5, we can now visit 5. And similarly, we then visit 6, 7 and 8. Okay, so that's the in-order traversal of the tree. And then there is another traversal called pre-order traversal, which is slightly different, where you traverse the current node first. So here we start out at 2 and we say that, okay, we're going to visit 2 first. So we visit 2 or print it or add it to a list. Then we traverse the left subtree and then we traverse the right subtree. So we visit 3 and 1. And then we come to the right side, we visit 5 and 3. So you can compare these two diagrams and see how in-order and pre-order traversal are different. Now these are very important for you to understand because they are great examples of different functions which have very similar implementations, but there are just 1 or 2 things you will need to change. And these are recursive as well. So do understand the subtle difference between them. And second, they are very commonly asked in interviews. You will most likely face some coding assignment or an interview where you will be asked to perform a traversal of a binary tree. And then finally, there's another traversal called the post-order traversal. And I'll let you guess how it works. You can also look it up. And here's an implementation of in-order traversal. Now it may seem a little complicated, but it's actually pretty straightforward. So let's look at it here. What we do is, given a node, we first traverse the node's left subtree. Then we create, so that should return a list of all the keys. And then we create a list with just the node's key. So we get the list of keys from the left subtree with the in-order traversal. Then we add to it the current node's key. And then we call traverse in order with the right subtree, and that recursively keeps adding these keys, each one. And the end condition, so the terminating condition for the recursion is when we hit none. So when we hit a node which does not exist, so that means we come there from a parent which does not have a left or right child, then we return the empty array. Okay, so let's try it out with this tree. So this is the tree we have, and we just saw its traversal. Now, if we traverse the tree in order, we get the values 1, 3, 2, 3, 4, 5, 6, 7, 8. And we can verify here. We have 1, 3, 2, 3, 4, 5, 6, 7, 8. So that was the in order traversal of a tree. Now, the exercise for you is to print the pre-order and post-order traversal of the binary tree. And you can test your implementations by making submissions to these problems on leetcode.com. Okay. So that was our discussion about traversals. Another thing that you may get asked commonly is writing functions to calculate the height or the depth of a binary tree, and then writing a function to count the number of nodes in a binary tree. Once again, these can be expressed recursively as well. Now the height of a tree given a node is simply 1 plus maximum of the height of the right subtree or the left subtree. The height of the tree is defined as the longest path from a root node to a leaf. So you can see that the longest path from a root node to the leaf is of length 4. So 2, 5, 3 and 4. And the way to get the length of the longest path is by checking the max of the left height, right height, and then adding 1 to it. And of course, the terminating condition here also is if you hit a node that does not exist, you return 0. So that's how you get the height of a tree. and you can check that the height of a tree is 4. Then here's another function to count the number of nodes in a tree. Once again, really simple. All you do is this time, instead of checking the maximum, we simply get the size of the left subtree, get the size of the right subtree, add them and add 1 to it. So here you can see that there are 9 elements in this tree, 3, 6 and 9. So we get tree size of tree as 9. Now here are a few more questions relating to the path lengths in a binary tree. So you can just check. There's a concept of maximum depth and minimum depth, and then there's also the concept of a diameter. So you can try out both of these. Now, as a final step, what we can do is we can compile all the functions we've written, all the methods as methods within the tree node class itself. And this technique is called encapsulation, where we are encapsulating the data as well as the functionality related with the data or the data structure within the same class. And this is really good programming practice. So as you write more code, try to think about how you can create these classes with not just the information inside them, but also with the relevant methods inside them. Okay, so we've now added the methods height, size, traverse in order, display keys, toTuple, and we've also added these methods str and repr. And remember quiz 1, you can go on LinkedIn and post an answer to what these functions do. And finally parse tuple as well. So all of these functions are now added within the class, and you can try it out here. So for instance, here we have a tree tuple, and we can call tree node.parseTuple to convert this tree tuple into a tree. So you can see that now we are also representing the binary tree itself using this tuple like representation, but we can also display it in this hierarchical structure using display keys. Then we can check the height using tree.height. We can check the size using tree.size, and we can traverse the tree in order using traverse in order, and we can convert the tree to a tuple using tree.toTuple. So do create some more trees and try out the operations that we've just defined, and you can also try adding more operations to the tree node class. And before continuing, we can just save our work. So I'm just going to import Jovian and run jovian.commit. So that concludes our discussion on binary trees. Next, let's talk about binary search trees. Now, a binary search tree or a BST is a binary tree that satisfies these two conditions. The left subtree of any node should only contain nodes with keys less than the current node's key. And then the right subtree of any node should only contain nodes with keys greater than the current node's key. And we can see that this is, let's just copy this over. So we can see that this tree here is actually a binary search tree, and you can verify that these two properties hold for each of these nodes. And it should follow from these two conditions that every subtree of a binary search tree must also be a binary search tree. So I'll let you verify that if you pick up any subtree inside, so you pick up any node and you see the tree under that node, you will see that it is a binary search tree. So here are some questions that are often asked relating to binary trees and binary search trees, and we've lumped them together because we'll answer them with a single function. So here's a function that you might be expected to write. So write a function to check if a binary tree is a binary search tree, which means ensure that these two conditions hold. And second, write a function to find the maximum key in a binary tree. So this could be a generic question, finding the maximum key. And here's another question that you might face. Write a function to find the minimum key in a binary tree. So what we will do is we'll answer all of these questions together with a single function called isBST. So isBST takes a node, and then isBST returns three things. So if you look at the return value, it returns whether the node and the tree under that node is a BST. So here, this is going to be the value determining, it's going to be either true or false, telling us whether the tree under that node with that node as root, is that a BST? It also returns the minimum key from that entire tree, and it also returns the maximum key from that entire tree. Now, why are these two useful? We'll see in just a moment. So the way we calculate isBST node is by actually looking at the left subtree and the right subtree recursively. So we call isBST on the left subtree of the node, and we call isBST on the right subtree of the node. So we get back three values, which is the left subtree a binary search tree? Is the right subtree a binary search tree? Is the minimum key in the left subtree, the minimum key in the right subtree, and then the maximum key in the left subtree and the maximum key in the right subtree. So now what we can do is we can say is BST node. So is the entire tree a binary search tree? Well, if the left subtree is a binary search tree and the right subtree is a binary search tree, and then we verify these two properties, which is the maximum key in the left subtree is either none, which means that there is no left subtree, or the current node's key is greater than the maximum key. And the minimum key in the right subtree, the smallest key in the right subtree, is either none, which means that there is no right subtree, or the minimum key in the right subtree is greater than the current node's key. So that this was condition 1 and condition 2. And that tells us whether this entire tree is now a binary search tree. And then finally, we can also calculate the minimum key and maximum key simply by computing the minimum of the left minimum, node.key, and right minimum. And the maximum can be calculated by checking the maximum of the left maximum, node.key, and right maximum. Okay. So what we return from the isBST function is whether a node and the tree rooted at that node is a binary search tree, and then the minimum and maximum key out of it. So if we look at this tree right here, let's verify whether this is a BST. And well, before we check, we can probably tell that it's not, because you can see that 3 appears as a left subchild of 2, but 3, the key is greater than 2, and that's a problem. So this is a violation of the property. Elsewhere, this property is satisfied. You can check any other node here and you will find that the left subtree is always smaller than the right than the node, and the right subtree is larger than the node. So let's check, is BST tree 1? It's not. So that's false. Now on the other hand, this tree is a BST. This is the tree that we've been looking at all this while. So once again, we can create this using tree node.parse tuple, and note that the keys can, the way we've implemented tree node, keys can not only be numbers, but they can also be strings. So we don't need to change anything here, and that creates tree 2. And we can even display tree 2. So if we do tree2 dot display keys, you can see that it has this structure where Jadesh is at the center, and then on the left you have Biraj, on the right you have Sonaksh, Biraj and Sonaksh, then you have Akash, Hemant, Siddhant, and Vishal. And this is a BST. So you get back true here, and the smallest value here is Akash and the highest value is Vishal, as you can verify in alphabetical order. So that's pretty handy. Now we have a way to check if a binary tree is a binary search tree. And this is again a very common interview question that you might face. Next, remember that we need to store not just keys, but also user objects within each key, within our BST. So what we do is we'll define a new class called BST node to represent the nodes of our binary search tree. And BST node will not only have the key, but in the constructor, it can also accept a value, and this is optional. So we will set the key and we set the value. We will also set the left and right. Apart from this, we also set another property called parent, and the parent will point to the parent node. So for instance, if this node is the left subtree of this root, then the parent of Biraj will point to Jadesh. And this will be useful for upward traversal. Now, if you're given a pointer to a node and you have to go back and find the root of the tree, the parent will be helpful there. So this is our BST node. And let's try to recreate this BST right here with usernames as keys and user objects as values. So first we create level 0. So level 0, we create BST node. Now the key is jadesh.username, which will be just the string Jadesh. And then the value will be the Jadesh user object. So we've created that, and we can check its key and value. You can see that Jadesh is the key and then the user object is the value. Let's create level 1. Now level 1 is, we set tree.left to BST node, Biraj.username and Biraj. Now, one other thing that we should do here is once we set it, we should set tree.left.parent to tree. And similarly, we set tree.right. So now tree.right is Sonaksh. So we set BST node with Sonaksh.username as the key and Sonaksh is the value. And then we can set tree.right.parent as tree. And now you can view these values. So now you can see that we've inserted Biraj and the username Biraj. We've inserted Sonaksh and the user Sonaksh here as keys and values respectively. Now the exercise for you to is then try to add the next level of keys and values and then verify that they were inserted properly. But you can see now that we now have a way to represent the data, both the usernames and the user objects in a binary search tree. So we're getting pretty close to the data structure that we want to create. And once again, we can display the keys of the tree by calling the display keys function. Now this is also rather nice. There's a good thing about Python that because Python functions are dynamic, because you do not need to specify the types of the objects while defining the function, the same display keys function can be used both with tree node and BST node classes. So all it requires is that the object of your class should have a property .key for it to be able to display the keys in this visual setting. And the same is true with most of the other functions that we've defined. In fact, any function we've defined for tree node will also work for BST node. Okay, so moving right along. Now we have a way to construct a BST, but it's a bit inconvenient to insert values manually, because what we're doing so far is we're manually checking whether we should insert a value in the left or the right. Rather, there should be a way to do it automatically. We should be able to call a function insert. And this is a common question as well. Write a function to insert a new node into a binary search tree. So we'll use the BST property to perform insertion efficiently. Once again, let's grab a copy of this tree here so that we can think about it easily. Okay, so now we have this tree, and let's say we want to insert a new user with the username Tanya into this tree. So first we start at the root, and then we compare the key to be inserted with the current node's key. So the current node is the root. So we compare Tanya with Jadesh, and we see that Tanya is greater than Jadesh because T comes after J. So obviously Tanya should not be inserted into the left subtree. Rather, Tanya should be inserted into the right subtree. So if the key is smaller, we recursively insert it into the left subtree, and if the key is larger, we recursively insert it into the right subtree. So then we encounter Sonaksh. Tanya is also greater than Sonaksh. T is greater than S. T comes after S. So once again, we recursively call insert on this subtree, the subtree rooted at Vishal. This time we notice that Tanya is smaller than Vishal, so T is less than V. So then we need to recursively insert in the left subtree, but there is no left subtree here. And this is the point at which we can create a new node and attach it as the left child of Vishal. So you can see that the node Tanya will get added here at this position in the tree. So here is a recursive implementation of insert, exactly what we just discussed. First we check if the key is less than the current node's key, and if that is the case, then we insert it into the left subtree. Then we check if the key is greater than the current node's key, and if that is the case, we insert it into the right subtree. And the ending condition is that if the node is none, which means we've hit a position where we do not have a left subtree and we need to go left, or we do not have a right subtree and we need to go right, then we create a new node. So we create new node equal to BST node, and then we return the node. So we return the node, and this is an interesting thing that we're doing here. We're returning the root node back from insert. So when we called insert with node.left, we get back the pointer to the left subtree. So we can set it back to node.left, and we can also set the parent of the left subtree to node. Okay, so this is just updating the parent. So just study this function carefully, see how it works. It does exactly what we just talked about, and it finally returns a pointer to the tree once again. So let's use this to recreate the tree that we had here. Now to create the first node, we can call the insert function with none. So initially we don't have a tree to begin with, so we just called insert with none. And remember that insert after performing an insertion, returns the pointer to the tree. So we call insert with none, and we want to insert the value jadesh.username, and we want to insert the key jadesh.username with the value jadesh. So that gives us a tree. And now the tree has one element. You can see tree.key and tree.value. And now the remaining nodes can just be inserted into tree. So now we call insert with tree and call it with biraj.username and biraj. Then we call it with sonaksh.username and sonaksh, akash.username and akash. And this way, so we're adding biraj, then we're adding sonaksh, then we're adding akash, hemant, siddhant, vishal. And see that we are not specifying exactly where these nodes need to be inserted. But you can see that once these nodes are inserted, then they are inserted in the right places. So Jadesh, you can see that the binary search tree property is preserved here. And also we've exactly replicated the tree structure that we had here. So the left subchild of Jadesh is Biraj and the right child is Sonaksh. For Biraj, the left child is Akash and the right child is Hemant, and so on. Now note, however, that the order of insertion of nodes can change the structure of the resulting tree. So for instance, if we insert all the nodes in the increasing order of username, so for example, here we are inserting Akash, Biraj, Hemant, Jadesh, Siddhant, Sonaksh, Vishal. So this is the lexicographic increasing order. And we try to display that tree. This is what we end up with. So we end up with an unbalanced or a very skewed tree. And you can see why it was created as a skewed or unbalanced tree. Well, let's look at it. So we start out with Akash. So we have a single node. And then when we try to insert Biraj, we realize that we need to go right. So we insert Biraj here. Then we try to insert Hemant. Then we realize that we need to go right from Akash and right from Biraj and go to Hemant. And then we keep going this way. So how you set up the root node and how you set up each subtree and the order in which you insert the nodes is very important. And that can create a huge skew within the tree. Now, skewed or unbalanced trees are problematic because the height of such trees is no longer logarithmic compared to the number of nodes in the tree, right? So earlier we had deduced that in a balanced tree, if containing n nodes, the height is log n or log n plus 1. And that makes the operations like insert, update, and find very efficient. But here, where you have a very skewed tree, the height can actually match the number of nodes. For instance, this tree has 7 nodes and it has the height 7. And in these skewed trees, once again, you may get back the fact that insertion, finding, and update can be order n, because you may have to traverse the entire height of the tree, which is equal to the number of nodes of the tree. And that may once again defeat the purpose of using a binary search tree in the first place. So maintaining the balance of a binary search tree is very important, and we'll see how to do that. So we've seen how to insert a node. Now the next thing is to find the value associated with a given key in a binary search tree. So once again, we can follow a recursive strategy here, similar to insertion. So we start from the top. Let's say we want to find the key Hemant. We start from the top and we compare it with the root node. Now here, if it matches the root node, we can simply return this node. If it does not, then we check whether we need to go left or right. Since Hemant comes before Jadesh, we need to go left. Then we encounter Biraj, and here we realize that we need to go right. And finally, we encounter Hemant and we return. Another option is that we have a value, let's say Tanya, which does not exist here. So if we try to search that, we may go in this kind of a direction and we end up at an empty place. So in that case, we simply return none. So you either find a node and return it, or you return none. So you can see here that if we call find tree with Hemant, we get back the details for Hemant. And very interestingly, because this is a balanced tree, we only had to take 2 steps and not go through the entire tree. And in the worst case, you can check that any path from the root to any leaf in a balanced tree will only be 2 steps long. And that's what makes it so convenient. Now, on the other hand, if we try to find the key Tanya, you can see that it's not found. Now try creating larger BSTs and try finding some more nodes. It's important to experiment with these operations once they're defined, because now it's simply a matter of calling the function. We've written the code for it. So experiment with it, try creating larger trees with multiple levels and dozens or maybe hundreds of nodes. Try generating some fake data, putting it into the trees and see how trees build up. And that'll give you a feel for how binary search trees work. Next, let's talk about updating a value in a BST. Now, updating a value is fairly simple. We already have a way of finding a node. So if you want to update a node, let's say we want to update the node Hemant, the key Hemant. And here we want to update it to this value, which is the new value of the user Hemant. And we're changing the name and we're changing the email here. So we first find the node, and if the node is not none, then we simply change the value at that node. It's as simple as that. And what we're also seeing is we're reusing the find function here. And this is a good practice to always incorporate into your programs, into your functions. Whenever you find yourself copy pasting some code and maybe changing one or two things here and there, think about whether you can extract that piece of code into a function and then reuse that function. So always try to make your code more and more generic. The less code you write, the less there are the chances for errors, the easier it is to understand, and the smaller your functions become. So write small, reusable, generic functions whenever you can. And this is a principle called the DRY principle or the DRY principle, which stands for don't repeat yourself whenever you're writing programs. So in update, we are not repeating ourselves by using the find function to find the right node and simply updating it by setting its value. So let's update Hemant here to the new value. And you can see that now we have the updated data here. So we have Hemant J and Hemant J at example.com. Now the value of the node was successfully updated, and you can easily check that the time complexity of update is same as that of find. Now finally, we have the last operation that was required, and this was to write a function to retrieve all the key value pairs stored in a binary search tree in the sorted order of keys. This is a question that you might face once again, and this is simply the in-order traversal. It's a different way of stating the in-order traversal. Now, what you will have to figure out or reason about is why the in-order traversal of a binary search tree produces a sorted array of or a sorted list of keys. Think about it. So here's the list all function. All we do here is we call list all on node.left, and then we call list all on node.right, and in between them, and these give us two arrays. So we assume that list all.node.left gives us the list of key value pairs from the left subtree in sorted order. Similarly, here we get the list of key value pairs from the right subtree in sorted order, and between them, we simply insert this key value pair from the current node, and recursively, it automatically fills out the entire array. And this is the end condition. Where we encounter an empty node, we simply return the empty array. You can see now when we pass in this tree, we get back the list of users, key value pairs arranged by the sorted order of keys. Now here's an exercise for you. Determine the time complexity and space complexity of the list all function. Now you can do this for a balanced tree or an unbalanced tree. And here's a hint, it will not make a difference. But think about it. So once again, let's save our work. And now we've talked about binary trees and operations on binary trees. Now the next thing is to look at balanced binary trees. And this is once again a very common question that gets asked. Write a function to determine if a binary tree is balanced. And here's a recursive strategy to do this. In fact, this is really the definition of balanced binary trees. The left subtree should be balanced. The right subtree should be balanced. And the difference between the heights of the left and right subtree should not be more than 1. Okay, so this is an important thing. Now, when we're looking for balance, we're not always looking for perfect balance, because it may not always be possible to create a tree with perfect balance. Because to have a perfectly balanced tree where for every node, the left subtree and the right subtree have the exact same height, you will have to fill out all the nodes at all the levels. and that can only happen for certain numbers. For example, you can have one node which satisfies this property, or you can have a tree with 3 nodes which satisfy this property, or you can have a tree with 7 nodes which satisfies this property, but you may not be able to get a tree with 6 nodes to satisfy that property. For instance, if you remove Vishal here, you will see that the left subtree and right subtree of this node Sonaksh will not be of equal height. That's why for balancing, we relax the criteria slightly. We simply need to ensure that the difference between the heights of the left and the right subtrees is not more than 1. So here's the code for is balanced. Once again, pretty straightforward, but we will return 2 things here. This is balanced will not only return whether the tree node is balanced, it will also return the height of the tree which is rooted at that node. So the way we implement it is first calling is balanced on node.left and then calling is balanced on node.right. And by the way, this is exactly how we implement recursive functions as well. Sometimes we write the recursive function's signature, then we immediately write the return value, and then we assume that a recursive call is going to return these values. So a recursive call is balanced node.left is going to return whether the left subtree was balanced and the height of the left subtree. And then we assume that is balanced for node.right is going to return whether the right subtree is balanced and the height of the right subtree, because that's what we return here. Then the entire tree is balanced if the left subtree is balanced and the right subtree is balanced and the absolute value of the differences in their height is less than 1, which means the height L minus height R is either -1, 0 or 1. And finally, we calculate the height of the tree itself, which is simply 1 plus the maximum of the height of the left subtree and the right subtree, and we return it. So that's how you implement a recursive function or think recursively. And there's one last thing, which is the end condition. And the end condition, although it's often the last thing you think about, it's the first thing that you have to put in. The end condition is to check whether a node is none, because as we call node.left, you may not have a left subtree, so you may call is balanced with none. And if the node is none, we simply return true, because an empty tree is balanced by default because there's no imbalance there, and its height is 0. So that's our is balanced function. It's just 4 or 5 lines of code. But if you are not able to reason about recursion easily, you may get stuck with this and you may spend an entire 45 minutes trying to write this function and debug it. So always try to think in recursive terms, and that's why it always helps to write down what you want to do in plain English so that you can determine what should be the inputs and outputs to your function. Maybe also have some test cases ready and then start implementing your function, and it becomes really easy. So this tree, for instance, is balanced. Here you can check is balanced, you get back true. But this tree here that you're looking at, this is not balanced. So this was tree 2. And if we check is balanced here, you get back false. So here you also get the height of the tree, which is 3. And here you get the height of the tree, which is 7. Now here's another tree. Is this tree shown here balanced? Why or why not? Now create this tree and check if it's balanced using the is balanced function. So there's another concept called complete binary trees, which is slightly similar to balanced binary trees, but it's a slightly stricter criteria. So you can check out this problem here. And you simply need to modify the code for is balanced slightly to get the code for complete binary trees. So do check out this problem on leetcode.com. All right, so we've looked at binary search trees and we've looked at balanced binary trees. Now let's bring them both together into balanced binary search trees. And here's one question that you will face at some point. Write a function to create a balanced binary search tree from a sorted list of key value pairs. So you have a sorted list of key value pairs. So the keys could, for example, could be usernames, the values could be the user objects, and they are sorted by key, and you have a list, and you have to create a balanced binary search tree from it. And here's the basic logic, which is somewhat similar to binary search, which is something that we've covered in lesson 1. Do check it out. What we can do is we look at the middle element. For instance, if you have a list of 15 elements, then the element at position 7 counting from 0. The element at position 7 is the middle element. Now we can take the middle element and then create a new binary search tree with the middle element as the root node. Okay, so you make the middle element the root node, and then you take the left half of the list and use that to create a balanced BST and make it the left child of the middle element, the root node. And then you take the right half, which both of the halves will have 7 elements each. So if you take the right half and you create a balanced BST out of it and then make it the right child of the middle element. So that's the idea here. And how do you make a balanced BST for the left or right child? Recursion, right? So once again, here's a recursive solution. Make balanced BST takes data, which is a list of key value pairs. It takes a low and a high, and it also takes a parent, and we look at those. Now, low is set to 0 by default and high by default is set to the last index in the data. So we use that to get the middle index. So for instance, if low is 0 and high is 14, the middle index is 7. Then we get back the key and the value from the middle index. So we find data made, and that gives us the key and the value, for instance, the username and the user object. Then we create the root node. So we create the root node using BST node, and then we call make balanced BST on data, but this time from low to mid -1. So from the indices 0 to 6, and make that the left child of the root. And we called make balanced BST on the right node. So on the right half, so from mid +1, so which is index 8 to 14, and we make this the right subtree, and then we return the root. And that's it. That's pretty much it. The only thing that we might need here is the terminating condition. When low becomes less than high, which means that we have no more elements to create trees out of, we simply return none. So the left or right subtree for the parents of those nodes gets set to none. So that's your makes balanced BST function. We also have this other thing called parent going around, and this I will let you figure out what the parent does here, but this is the basic idea. So here is a list of key value pairs. You have key value pairs sorted in the increasing or lexicographic order of keys. And we're calling make balanced BST with data, and that gives us a tree. And let's view the tree here. So there you go. Now we've created the tree perfectly as we wanted it. Jadesh is at the center, and we have Biraj Sonaksh on each side, and then the appropriate nodes on each side as the children of those nodes. Now recall that the same list of users, when inserted one by one, resulted in a skewed tree. Here we are getting the list of users, username and user from data, and inserting them. And you can see calling display keys on tree 3 returns a skewed tree. Okay. So whenever you have a sorted array and you want to create a balanced BST, the way to do it is to start from the middle out. Now, finally, one other question you may be asked is to balance an unbalanced binary search tree. And this is pretty simple at this point, and this is kind of a trick question, because if you were given this question directly, you may not be able to think about what to do. How do you balance an unbalanced binary search tree? But now that we have a way to create a balanced binary search tree from a sorted array of key value pairs, and we have a way to get a sorted array of key value pairs. So now it simply becomes calling the sorted array. So calling list all on the node, which is also the in order traversal. So doing an in order traversal of the binary search tree, which gives us a sorted array of key value pairs, and then passing that into the make balanced BST function. Okay. So that's the trick here. It's a two-part question. And once again, we see the benefit of reusing our functions here. Now balancing an unbalanced BST now becomes a single line of code. That's very nice. So we create a tree here with the value none, and now we insert into it the values one by one. And you can see that that creates a skewed tree because we are inserting the values in increasing order, lexicographic order. So we keep adding right children and we never add a left child. But then we call the balanced BST function, which internally takes this gets in order traversal. So the in order traversal lists all the keys and key value pairs in sorted order. And then we call the make balanced BST function, which starts from the middle and then creates a balanced binary search tree out of it. So there you see, this is how you balance a binary search tree. And what we can do now to maintain the balance as we grow our data structure is a simple thing that we can do is to insert, to balance the tree after every insertion. And that brings us to the complexities of the various operations in a balanced BST. So if we are doing if you're doing an insertion, that takes order log n, because now if a tree is balanced, its height is order log n. So for insertion, you may have to traverse a path from the root down to a leaf, and that path can be of length at maximum equal to the height, which is order log n. But if we are also doing a balancing with every insertion, then we also have an order n term added here, and order n plus order log n, because log n becomes much smaller than n as n grows. So order n plus order log n is the same as order n. So that makes insertion order n. Finding a node becomes order log n. Updating a node becomes order log n. And you can verify that listing, getting a list of all the nodes, is order n. So what's the real improvement between order n and order log n? So let's think about it. If you're looking at 100 million records, then log to the base 2 of 100 million is about 26 or 27. So it only takes 26 operations to find or update a node within a balanced BST, as opposed to 100 million operations. So you can see here a 26 or a loop of size of length 26, and we're doing some operation inside it, only takes about 19.1 microseconds. That is, 1 microsecond is 10 to the power minus 6 seconds. On the other hand, order n involves looping through the entire list, so looping through 100 million numbers rather than 26, and that obviously takes far longer. And we saw that it took about 10 seconds, right? About 9.98 seconds. So to find and update, finding and updating a node in a balanced binary search tree is 300,000 times faster than our original solution. And all we've changed here is the data structure. And that's the importance of data structures, because now each user will be able to view their profile in just 19.1 microseconds. At least that part of the request will take only this long. So the user experience will be better, and your CPU will be busy for a shorter time. So you will be able to serve not 8, but hundreds of thousands of users every second. And finally, your hardware cost will also be far lower, because now your CPU is busy for a lesser time. So you do not need to use a very large machine, or you do not need to use too many machines to support hundreds of millions of users. And that is the benefit of choosing the right data structure. Now there's one tip here. How do you speed up insertions? So what we may do is we may choose to perform the balancing periodically instead of at every insertions. For example, we can balance for every 100th insertion, or every 1000th insertion, or every 100,000th insertion, whatever, and that's where we have to balance how often do we need to insert things versus how often do we need to restore the balance. Another idea is to do the balancing maybe periodically at the end of every hour. So for a second or two, there may be a slight dip in the performance because you may be performing the balancing, but even that, there's a way to do it. So you can take a copy of the tree and then balance it, and then simply replace the pointer to the original tree. So there are many other tricks that you can apply. And in fact, there's also an algorithmic trick which brings insertion and balancing together into an order log n operation, which we look at right at the very end. So stay till the end. But before we do that, let's come back and answer our original problem statement. So remember now, as a senior backend engineer, you are tasked with developing a fast in-memory data structure to manage profile information, username, name, and email for 100 million users. And it should allow insertion, find, update, and listing the users by username, all as efficiently as possible. And to answer this question, instead of creating a user database class, we can create a generic class called tree map, because we have been making things more and more generic as we have gone along. So let's define a function called tree map, which internally stores a binary search tree, a balanced binary search tree inside it. So when we initialize the tree map, we set self.root to none, which means we have not created a tree so far. And then instead of defining functions insert, update and delete, we are going to use some special functions in Python classes. So we're going to use the function set item. We're going to use the function set item here, and set item is just like insert, except it is a combination of both insert and update. So to set item, we will pass a key and a value. And of course, self will refer to the tree map object itself. So the first thing we do is we get the root, which is basically the binary search tree that we are storing internally here. So we get the binary search tree, and then we look for the key inside the binary search tree. So if the key is found, so if we find the node in our tree, then we come into this else position and then we simply update its value. And if we do not find the node, so which is what happens initially, because initially our self.root is none. So when you call find with none and pass a key, you get back none. So then we first set self.root by inserting the key into the tree. Okay. So if a key exists within our binary search tree, then we update it. And if the key does not exist within a binary search tree, then we insert it into our binary search tree. Okay. So we've combined insert and update into the single operation called set item. And similarly, we define another operation called get item. This is the find operation. All we do here is we find the node inside self.root using the find function we had defined earlier. And if the node is present, if it is found, then we return the value of the node. Otherwise, we return none. So given a key, we retrieve the value. And then we define one last function called iter, and this is the replacement for our list all function. So what we do is we simply say we call list all on self.root. So that gives us a list of key value pairs. And then we have this special syntax. We say x for x in this list, and we put these round brackets around it. So what this round brackets around it does is that this creates a generator out of it. So now this is no longer list, but this is a generator. And a generator is something that you can use within a for loop. So the iter function will allow our class to be used directly within a for loop, and we'll see the example in just a second. And finally, we have another function called __ len. So remember, there are double underscores here. So there's double underscore set item, double underscore get item, double underscore. Similarly, double underscore len, double underscore. Here we simply return the size of the self.root. So here we simply return the size of the binary tree. And then we have this function called display. This is going to simply display the keys. Okay, so now we've defined this tree map structure, and it has all of these funny looking methods like we know init, but what about all of these? But we'll see what these do in just a moment. And we know what the functionality is, but you may be wondering why we've defined them like this. So the reason is these are special methods that are treated specially in Python. So here's how you can use them. Let's first get a list of users that we'll later insert into a tree. Let's get a tree map. So we instantiate the tree map function, the tree map class, and that gives us a new tree map. Inside it, there is no binary tree. You can check. If you check tree map.root, you will see that it is none. There's no value here. And if we try to display it, you can see that this tree map is empty. Then to insert, instead of calling tree map.insert or instead of calling tree map.__ set item, we can use this indexing notation. So we open these square brackets and we put in the key that we want to insert. So if we want to against the key Akash, which is the string, if we want to insert the value Akash, then we simply say tree of Akash is Akash. And similarly, tree of a certain key with the indexing notation set to this, right? So this is going to first look for the key as we have defined in set item. If it finds the key, then it is going to update the value for the key. If it does not find the key, then it is going to insert that key value pair as a new node into our tree. So let's check it out now. And let's see here, if we now check tree map.root, you will see that now it is a BST node. And if we try to display it, you can see that now it has a structure Jadesh, Sonaksh, and Akash. Also note that this is a balanced tree. And if you go back here to set item, you will notice that whenever we insert, right after this, we also balance the tree. And now you can change the logic here so that we do the balancing not after every insertion, but maybe after every 100 insertions. So you may need to track somewhere what is the current insertion counter. And when it gets to 100, only then do the balancing and then set the counter back to 0. So that's an exercise for you. Perform the insertion or perform the balancing only at certain intervals. And here's a way to retrieve an element. So the retrieving an element is also now really simple. You just call tree map with Jadesh as the index, and that gives you the value if it is found. And if it is not found, it simply returns none. Now, because we've defined the function underscore underscore len underscore underscore, so you can see here that has the value 3, because that now we can use it with the len function, which is used for lists and dictionaries. And let's add a few more things. And let's set the values and let's see here. So you can see all this works exactly as expected. Now we are able to set values, we are able to update values, we are able to display the tree. It is remaining balanced. And remember I mentioned that you can use this in a for loop. So you can now put the tree map directly into a for loop. And what this will do is, because we have defined the underscore underscore iter function, and the iter function returns a generator. So now you can use this in a for loop and you get back the key value pairs from the list all function that was used inside iter. You can print the keys and the values. And in fact, if you want to convert it to a list, all you need to do is pass it into the list. And once again, because this is a generator, because this is an iterable, this is now an iterable class, and you've defined that the way to iterate over this class is to get elements out of the key value pair list. So when you call list, you get back this list of key value pairs. Okay, so now we've made it a very Python friendly class. Instantiating it is very easy. We simply create a new tree map. Adding values is very easy. We simply use the indexing notation. Removing elements is very easy. Finding elements is very easy. We simply use the indexing notation. Updating elements is the same as inserting. We can also check the size of the tree quite easily using the len function. And then we can also iterate over the keys, iterate over all the users in a for loop quite easily. And we can also update values. As you see here, values have been updated. Now, the purpose of doing this is to make it easier for other people to use this data structure. Now, as a senior backend engineer, you may have designed this data structure and you may have implemented binary search trees inside it, but it's not important for other people on the team or other people using your data structure to know what the internal implementation is. What's important for them is to be able to use it easily. So that's why always think carefully about the interface or the API of your functions or of your modules or of your classes. Try to make them as Python friendly as possible. This was something that will be appreciated in interviews and by co-workers. So make them Python friendly so that when people want to use something you've created, it is extremely intuitive. And they do not need to really understand the underlying details. For instance, I could be using this class and I could have no idea that it is a binary search tree. All I know is how to insert and how to get a value out of it. And I know that it is super efficient because you have designed it. And I don't need to worry about the internal details. So encapsulation and good APIs are very important skill to have, to cultivate. So do that as you work on programming problems. Now, once again, let's save our work before committing. Now I did tell you that there is a way to create self-balancing binary trees. And a self-balancing binary tree remains balanced after every insertion or deletion. And in fact, several decades of research has gone into creating self-balancing binary trees, and not just binary trees, but other trees as well, which are not binary in nature. And many approaches have been devised, for instance, red-black trees, AVL trees, and B trees. So here's an example. This is an AVL tree. So here, whenever a node goes out of balance, we rotate the tree, and you can see visually what we're doing here. Now, whenever you see that there is an imbalance in the tree, we rotate it. And how do you do this? We do this by tracking the balance factor, which is the difference between the height of the left subtree and the right subtree for each node. and then rotating unbalanced subtrees along the path of insertion or deletion to balance them. So you can see the balance factor is 0 right now, the balance factor becomes 1 and the balance factor becomes 2. Then we rotate it to set the balance factor back, and then the balance factor here becomes -2. So here we do a right rotation. Here the balance factor becomes -2 here and -1 here. So here we do 2 rotations. So there are 4 cases in total. There's the left-right case, the right-left case, the left-left case, and the right-right case. All 4 cases were demonstrated here as well. And then you may need to do this rotation, not just once, but you may need to do this multiple times along the path of insertion. So when you insert a node and that node creates an imbalance, then you need to work backwards. So you need to keep going from parent to parent and keep rotating nodes whenever you need to rebalance them based on the updated balance factor of each node. So it seems a little complicated, but it's actually not. It's just that there are multiple cases to handle. So you will need to write a couple of helper functions. You'll need to write a function left rotate, which rotates node left while still preserving the binary search tree property. You will need to write a function right rotate, which rotates the function, which rotates it to the right while preserving the BST property. And then in the insertion, you will also need to perform the rotation at the right places, and you will need to track the balance factor inside each node. So there are a few things to work out here. And don't worry, you will normally not be asked to implement an AVL tree within an interview or within a coding assessment. So you do not really need to learn the implementation, but it's nevertheless a very interesting data structure to study. And here are a couple of resources you can check out. So you can check out this YouTube video, which explains it very wonderfully. And you can check out this implementation on geeksforgeeks.org. And the important thing for us to take away here, and which is something that you may be asked, if not the implementation, but just the complexity. The important thing is that each rotation takes constant time, and at most log n rotations may be required, because if you are starting with a balanced tree and you're inserting a new node, then you may traverse a path of height at most of length at most log n. So you may need to perform at most log n rotations, maybe twice of that. So what that means is in order log n time, you will be able to insert and maintain the balanced property of a binary tree, right? So you do not need to recreate the entire tree again. And that makes your tree very efficient, because now when you're working with 100 million records, inserting will also take 20 steps, and finding will also take 20 steps, and updating will also take 20 steps. And all of these will work in microseconds. So that makes your data structure very efficient. And with that, we conclude our discussion of binary search trees. So here's a quick summary. We looked at this problem of creating a data structure which allows efficient storage, retrieval, and updation. Also efficient iteration in a sorted order. We first started out with a list of values sorted by the keys. And we realized that that was probably not the right idea, because we are working with really large number of records. Then we created this binary tree structure. So we looked at binary trees, we looked at how to create them, we looked at easy ways to visualize them, easy ways to create them from tuples. We looked at how to calculate their heights, their sizes, how to traverse them in order, pre-order, post-order. We then looked at binary search trees, which have this property that the left subtree has keys that are smaller than the root node's keys, and the right subtree's keys are larger than the root node's keys, and that property holds at every subtree. And that makes it really easy to locate a specific element or find the position to insert an element. So we created binary search trees. We created the operations, insert, update, find, and list all in a binary search tree. We also determined ways to check if a binary tree is a binary search tree or not. Then we talked about balancing, and we saw how to create balanced binary search trees. And binary search trees form the basis of many modern programming language features. For instance, maps in C++ and Java are binary search trees, and data storage systems like file system indexes or relational databases also use something called B trees, which is an extension of binary search trees. So it's very important to know about binary search trees, even if you may not ever need to implement them. You may be asked about them, and in many cases, you may need to pick a binary search tree as a data structure for a problem like we did in this case. Now you may wonder if dictionaries in Python are also binary search trees. Well, they're not. Dictionaries in Python are not binary search trees. So we will soon release an assignment that you can find on the lesson page, and you will work on hash tables in the assignment. And here are some more problems that you can try out. So you can try to implement rotations and self-balancing insertion. You can try to implement the deletion of a node in a binary search tree. That's slightly more complicated, because what do you do if you have to delete a node that has both a left and right subtree? You can try deletion with balancing if you really are up for a challenge. Here are a couple more. Finding the lowest common ancestor of two nodes in a tree. So the common node which is a common parent of both nodes. Here you can use the parent property. Finding the next node in lexicographic order. So given a node, how do you find the next node? What's its complexity? Or given a number k, how do you find the kth node in a binary search tree? So to do this, you will have to employ some clever tricks. And then there are a couple more resources here. You can open up these and find more questions. The important thing to take away is that almost all of these will involve some form of recursion. So you will either work with the left subtree or the right subtree or both. And some of them may also require you to store additional information within the node. For instance, for this one, given a number k, find the kth node. This may require you to store the size of each balanced binary search tree in each node. So what to do next? You should review the lecture video and execute the Jupyter Notebook, experiment with the code yourself, then complete the assignment, hopefully. The next lesson is called Divide and Conquer and Sorting Algorithms. This is data structures and algorithms in Python, and I will see you next time. Thank you and goodbye. Let's look at assignment 2 of data structures and algorithms in Python. The topic of the assignment is hash tables and Python dictionaries. So let's get started. The first thing we'll do is go to the course website, pythondsa.com. And on the course website, you can find all the lessons and previous assignments. Now, we are looking at assignment 2. So you may want to open that up. And assignment 2 is based on or inspired from some of the topics discussed in lesson 2. So you may also want to watch lesson 2 and complete the notebook before you work on assignment 2. Let's open it up. Now in this assignment, you will apply some of the concepts learned in the first 2 lessons to implement a hash table from scratch in Python. That's very interesting. And hash tables are a very important data structure. They're present in pretty much every programming language and are a common topic discussed and asked in coding interviews. So we'll see how to implement them from scratch. And one of the central problems in hash tables is called collisions. So we'll see how to handle hashing collisions using linear probing. And we will also replicate the functionality of Python dictionaries. So Python dictionaries are actually implemented using hash tables. So we'll see how to replicate the way Python dictionaries are created and used and modified, and the way we access keys and iterate over keys and set values and change values and so on. So we'll pretty much re-implement the Python dictionary. Now we have an assignment starter notebook here, so we can click on view notebook to open up the notebook. Once again, this is a Jupyter notebook, and as you work through the notebook, you will find question marks in certain places. To complete the assignment, you have to replace all the question marks with appropriate values, expressions, or statements to ensure that your notebook runs properly end to end. Okay, so make sure that you run all the code cells, do not change any variable names, and in some cases you may need to add code cells or new statements. And since you'll be using a temporary online service for code execution, keep saving your work by running jovian.commit at regular intervals. There are some optional questions. They are not considered for evaluation, but they are for your learning. Okay, so let's run the code. Now, the recommended way to run the code is using free online resources, Binder specifically, but you can also run it on your computer locally. So we're going to click run and click run on Binder. Once again, this may take a few minutes sometimes depending on the current traffic on the platform. There we have it. Now we have the Jupyter notebook running. The first thing I like to do is click kernel and restart and clear output so that we can execute all the code cells and see their outputs from scratch. I'm also going to hide the header and the toolbar and zoom in here a little bit so we can see things a little better. The first thing we will do is set a project name, import the Jovian library, and run jovian.commit. This will allow you to save a snapshot of your work to your Jovian profile. So now you have a copy of the assignment starter notebook. Any modifications that you make every time you run jovian.commit will get saved to your personal copy, and it is this personal copy that you will submit at the very end. So let's talk about the problem statement. In this assignment, you will recreate Python dictionaries from scratch using a data structure called hash tables. And dictionaries in Python are used to store key value pairs. So keys are used to store and retrieve values. And here's an example. Here's a dictionary for storing and retrieving phone numbers using people's names. So we have a dictionary called phone numbers, and the way you create a dictionary is using this special character, the brace or the curly bracket as it's called. And then in a dictionary, you have these key value pairs. So this is one key value pair where you have a key. The key in this case is a string Akash. And here you have a colon. And then here you have a value. The value in this case is a phone number. So that's how you create a key value pair, and comma separated key value pairs is what you need to create a dictionary. You can see once the dictionary is created, it is displayed in the exact same way. And then you can access a person's phone number using their name. So if we have the variable phone numbers and we use the indexing notation, so this is the square bracket, and we pass in a key here, we get back their name. And you may wonder what happens if the key is not present. The great thing about Jupyter is you can insert a new cell. Like you can just click insert cell below, or you can use the keyboard shortcut B as I just did and check maybe, let's check the key Vishal. Okay, and you get back a key error. And you may also wonder what happens if, is it case sensitive? Does that matter? You can check it very easily. So a lot of the questions that you might get, a lot of the questions that you may want to even ask on the forum or look up online can be resolved simply by creating a new cell and typing out some code. Right? What happens if questions can all be answered by writing some code? So now let's add some new phone numbers. So this is how you create an initial set of phone numbers. This is how you access a phone number, and this is how you add new values. So adding new values is like accessing them, but instead of accessing it, you put an equal to, and then you actually set the value here. So we can add a new value here, the phone number for Vishal, and we can also update an existing value in a dictionary simply by accessing that value and putting an equal to and putting in a new value there. You can see now that the dictionary is updated to contain the new phone number 7878 and not the original phone number 948948. You can also view all the names and phone numbers stored in the phone number dictionary using a loop. So you can say for name in phone numbers. So when you put a dictionary into a for loop, you get back a key within each loop. You can see here that the name and the phone number here is displayed for you using the print statement. So those are some things that you can do within a dictionary. And dictionaries in Python are implemented using a data structure called a hash table. And a hash table uses a list or an array to store key value pairs and uses a hashing function to determine the index for storing or retrieving the data associated with a given key. So here's what it looks like. Here you have the key John Smith, and you have a function called hash, and the function hash takes any key and it returns an index within the list. So why do we use a hashing function? Well, one approach, as we've discussed in lesson 2, is we can store key value pairs in a list, and we can simply search through the list each time we want to look up the value for a key. But that is inefficient because that requires looking through potentially all the keys before we get to the key that we want, or maybe half of the keys. So that makes it an order n operation if n is the size of the list. That's pretty inefficient. We want something faster, and a hash function actually operates in constant time. So hash simply takes the key and it converts the key into a number. So in that sense, it gives you the index of the specific key value pair in constant time rather than order n. And that is what makes hash tables so efficient. right? So hash function does not require looping through the list. It simply takes a key, gives you the index, and you can simply then get the key value pair or the value from that index. Now your objective in this assignment is to implement a hash table class which supports these operations: an insert operation, a way to insert a new key value pair, a find operation to find the value associated with a given key, an update operation to update the value associated with a given key, and then list operation to list all the keys stored in the hash table. And here's where we are going to use Python classes. And there's a brief introduction to Python classes in lesson 2 of this course. So do check out lesson 2 if you want a refresher on Python classes. You have the class hash table. And inside the class hash table, you have a bunch of methods. Now the insert method, apart from taking the self argument, and remember that the self argument refers to the object of the class that will be created. So this is equivalent to the this variable in Java or C++. But these are the actual arguments of the method. The actual arguments are key and value. So the insert function or the insert method will take key and value. Then the find method will take a key. The update method will take a key and value once again. So the find method takes a key and your job is to return the value. The insert method takes a key and value, and you insert the key value pair into the hash table. Then you have the list all method, which is used to list all the keys from the table. So before we begin our implementation, let's just save and commit our work. So we're running jovian.commit here. Let's just run that once again. There we go. The notebook has now been committed. So what you can do is you can come back to this particular page and you can find this from your profile, and then you can click run to continue your work based on the modifications that you've already made. Okay, so we build a hash table class step by step. And the first step is to create a Python list which will hold all the key value pairs. Now remember that a hash table internally uses a list to store the key value pairs. And we will create a list of a fixed size. So we'll set this variable max hash table size of size 4096 initially. And we are going to create a Python list of this size. Now, how do you create a Python list of the size? And we want all the values to be set to none. So this is the way to do it. You can, of course, you can start typing none, and that would take a long time. Or you can use a simple technique. Just put in none times 4096. And that's one of the great things about Python. It is such an expressive language that creating a list of 4000 elements simply requires this single expression here. You can check that here. You can even check the length of the data list. Now, if the list was created successfully, here are some test cases. Here is one check that the length of the list is 4096. Here's another check, and we're simply picking a random value from the list 99 and just checking if that is equal to none. But if you really want to have a short test here, what you should be doing is you should be checking for item in data list, item equals none. Okay, and here's a trick you can do. You can write a word called assert, and what assert does is if this comparison is true, then it does nothing. It lets your code proceed as usual. But if at any point this comparison becomes false, then it throws an error. So let's see here. You can see here there was no error, so that means it worked fine. But if this comparison was wrong, so let's say if we had here, we wanted the item to be equal to 7. If you put it and data list does not contain the item 7 at certain position, then you will get an assertion error here. Okay. This is how you can create your own test cases by putting in assert. But the idea here is that whatever you try to do, make sure that you're adding some more test cases and not just depending on the test cases that are given here. Okay. These are simply to guide you in the right direction. Okay, so next up, we have a list. Now we need a way to store or insert key value pairs into a list. That's where the hashing function comes into picture. The hashing function is used to convert strings and other non-numeric data types into numbers, which can then be used as list indices. For example, if a hashing function converts the string Akash into the number 4, then the key value pair Akash and the phone number 7878787878 will be stored at the position 4 within the data list. And here's a simple algorithm for hashing, which can convert strings into numeric list indices. And a hashing algorithm does not have a single definition. You can come up with a hashing algorithm, and in fact, coming up with a good hashing algorithm is an area of research in itself. Now, of course, Python dictionaries use hashing that is inbuilt into Python, and that's a fairly optimized hashing algorithm that's probably the result of several years of research. But here's one very simple technique. We iterate over the string character by character, and then we convert each character into a number using Python's built-in ORD function. And you can see here that if you call ORD on the character X, you get back a number. It already gives you a way of converting characters into numbers, but not entire strings. That's why we need to iterate over the string character by character. Then we simply add the numbers for each character to obtain the hash for the entire string. It's a very simple technique. We just keep, if you have the number hello, we take the odd for hello, the odd for E, the odd for L, the odd for L, and the odd for O, and add them together. And since we want that number, the final result, to be an index or a position within the list, so we take the remainder of the result with the size of the data list, right? So it's possible that once you add the numbers together, you may end up with a pretty big number. But if you take the remainder with 4096 or the max hash table size variable, you get back a number that is smaller than 4096. So you can use just that remainder as the index. So let's first define a function called getIndex. All it does is it takes the data list and it takes a string, and it applies this hashing algorithm to return an index for that string, for that key. So for a character in a string, we need to convert the character to a number. So we convert the character from the string into a number by calling ORD on a character. Great. Then we update the result by adding the number. So we say result plus equals a number. Pretty straightforward. And that repeats for all the characters in the string, and then we get back the final result. Now that result may be longer than the actual size of the list, and this is where we may then want to check the size of the list. Okay, now remember, there's one, I could also have probably written max hash table size here, but that would be wrong, isn't it? Because we are passing in a data list here. We are passing in a data list, and although we have so far created a data list of size 4096, your function should ideally be looking at the size of the data list that you have here and not any global variables. So keep that in mind. And the right thing you should check here is len data list. And what this will allow is, now this will allow your function to work with data lists of different sizes, and not just the standard size 4096 that we have defined above. Okay, very important thing. Always make sure that your functions use the arguments that are passed into them, that they are generic, that they can work with any input and not just a particular input that has been defined earlier. Okay, so there you go. Now you have, this is our function getIndex that has been defined. And here are some tests. Now, if you pass in the data list and you pass in the empty string, because there are no characters, the result is likely to be 0. It's great. Here's another one. The result here is 585. Here's another one. The result here is 941. Great. Now, this is where you should be testing your function with some custom test cases. I'm going to create a new data list 2, and this is going to have the size none times 48. So this is only going to have the size 48, and I should be testing getIndex with this data list as well. So let's say we're looking at the key Akash. Now we know that, let's see, we can actually test this out here. What happens if you add ORD of A plus ORD of A plus K, A, S, and H? That number is 585, but since the size of the list is 48, what we should be getting back as the result is 48 divided by 585. So we should be getting, oh sorry, 585 and its remainder with 48, we should be getting back the number 9. This should be equal to 9. Okay, so let's check that if this is equal to 9, and indeed this is equal to 9. On the other hand, if we had max hash table size, you will see here that since we are not taking into consideration the actual size of the list that was passed into the function, we are getting back the value 585 because we are taking the remainder with 4096. Okay, so remember to take the result remainder with the size of the data list that was passed in. So this is one of the several gotchas in this assignment, and they're there for a reason, because this is something that you need to keep in mind. A function which only uses its arguments and does not depend on any external global variables or constants and things like that is called a pure function. Of course, a pure function also does not modify any external global variables. So it simply takes some arguments and returns the result, irrespective of anything else outside. So now we can, to insert a key value pair into a hash table, we can simply get a hash of the key. So here we have a key value pair, and we simply get a hash of the key by calling get index for data list and key, and we get back the index 585. And then inside the data list at the given index, we can simply set the key value pair as the element stored at that index. And the same operation can be expressed in a single line of code. So here we're calling get index for data list and Hemant, and that's going to give us an index. And we're going to then invoke a set at that particular index within data list, the element Hemant, comma Hemant's phone number. Now to retrieve or find the element associated with a pair, we can simply get a hash of the element, the value associated with the key. We can simply get a hash of the key and look up that index within the data list. So here we have the key Akash and we have the data list, and we call get index. So we get the index of the key Akash, and that gives us the index here. And we can then call data list and pass in the position IDX, and that should give us a key value pair. Remember that we stored a key value pair at the given index, so we should get back that value here. So now we know how to store a value. You get its hash for the key and you store the key value pair, and how to retrieve a value. So you get a hash for the key and then you retrieve the key value pair, and from there you can get the value. We can also list the keys. To list the keys, here is some special code we are using. So let's see, this is called list comprehension, and let's take a quick look at list comprehension. So list comprehension works like this. If you create a list Y from a list X, let's call this list 1 and list 2. Good variable names always help. So if you have a list 1 and you write this X for X in list 1, what does that do? That for X in list 1 fetches elements one by one from the list, and then here you can specify what to do with the numbers that were fetched. So right now I'm not doing anything, I'm simply returning that number, and then I'm putting the entire thing into a list. What this does is this creates a new list. So you can see this is a copy of the original list. What I could do is I could write X times 2 for X in list 1, and now I would end up with a list in which each element is the double of that particular element. I could also do X times X if I wanted. I could also call a function on it. Let's see what function we can call here. Let's maybe put in some numbers here: 1.3, 2.4, 3.2. So we could put maybe the function math.round x, or sorry, math.ceil. This is going to give us a ceiling. So 1.3 becomes 2, 2.4 becomes 3. So you can do any operation with each element of the list, and once you put that in a bracket and you have this for here, that's going to apply that same operation to the entire list. And this is called list comprehension in Python. It's a very powerful way to express complex operations on lists and dictionaries. And there's one final thing in list operations, which is the if condition. So for x in list 1 can be followed by an if condition, and the if condition can once again apply on x. So if x is greater than 3, let's say we put this condition, then what happens is we choose only those numbers from list 1 which satisfy this condition, x greater than 3. So that means we would skip 1.3, we would skip 2.4, we would get 3.2, we would get 6, we would get 7, and we would apply math.ceil to them, and that's how we get back 4, 6, 7. So that's list comprehension in a nutshell. So to get a list of keys, all we can do is for key value pairs in data list, if the key value pair is not none, remember that we have a lot of none values and it's a huge list. If the key value pair is not none, then we simply return kv0. So remember, if you have a key value pair, if you have like a key value pair that's Akash and a phone number, and you can also put, because these are tuples, you can also put a round bracket here if you want, but even without it, it's the same thing. That's a key value pair. So kv0 is going to give you the key, and kv1 is going to give you the value. So we simply get the key for those key value pairs in data list where the element at that position of the key value pair is not none. And that should not be called pairs, that should probably be called keys. You can see that the keys are Akash and Hemant. So that's how we can now use the getIndex function. And the next step for you is to complete the hash table implementation here by following the instructions given in the comments. So now you have this basic hash table class, and in this class you have a constructor. Now the constructor takes the object self, or this, and the self is going to point to the actual object or the actual hash table that gets created using the class, and then it takes a maximum size. Now what are we doing here? We want to make our hash table configurable. We don't always want to have 4096 elements in our internal list. We may need a hash table that can store more values, or we may need a hash table that can only store fewer values. So we are going to set a default value for it, which is the max hash table size. So if you do not provide this argument, by default it will create a list of size 4096, but we also want the option to specify a maximum size. Now you need to create a list of size max size with all the values set to none. Now you may be tempted to do this, but that would be wrong. Remember that always use the arguments to a function. Try not to depend on an external value or an external constant. So this would be wrong. You may also be tempted to do this data list, self.data list equals data list that we've already created. This would also be wrong, not just because you're not using the max size, but also because now you are tying this class implementation to a global variable, and that global variable is a list which can be modified. So if all the objects of this class, any number of hash tables that you create using this class, will all use the same data list, and that's not what you want. Each hash table that you create, maybe you have a hash table for phone numbers, you have a hash table for addresses, you have a hash table for something else. Each of them should have their own internal data list. And this is not going to create a copy of that original list. This is simply going to point to the original list. So what you want to do is you want to do none, and you want to multiply it with max size. There you go. This is the correct way to do this. Now we're looking at insert here. Now to insert, we did see that to get the index, all you need to do is you need to pass the key. And remember here you need to pass not data list but self.data list, right? Because now we want to use the data list that is stored inside this specific object of the class. We do not want to use the global data list. And this is something that is a mistake that we often make initially. I've still make this mistake where I have certain global variables defined and I'm using those global variables inside my class. Avoid doing that. Anything that you want to put inside a class object, you need to put inside self like we've done here. And then to access it, you need to use self dot to access that specific property or element or even method. So now we have self.data list, and we pass in the key and the data list into getIndex, and that gives us the index. Now the getIndex function was defined earlier. We've seen it already. Now we want to store the index inside the list. So we call self.datalist idx, and we want to store the key value pair there. So we can simply put in key comma value here. If you wish, we can also put in the brackets, but they are not necessary. And that's going to insert the key value pair. Now, how do we find the value associated with a given key? First, we get the index for the key. So we call getIndex on self.datalist and key. Then we retrieve the data stored at the index. So this would be simply self.datalist of idx. And then if the key value pair is not none, if the key value pair is none, well, there's nothing at that index, we can return none. Another option would be to also maybe raise an index error and with a message, etc, etc, but return none is good enough for now. Then if not, from the key value pair, we get back the key and the value, and then we return the value. Keep that in mind. If you simply return this, you would get an error, you would get an exception that may go unexplained. So whenever you are destructuring or you're trying to get two values out of a tuple, make sure that the tuple is not none, especially in this case, because we're starting with a list of nuns in a place where we're supposed to be storing key value pairs. So that's fine. Now update is going to be pretty much identical to insert. I don't see any difference here. So we can simply say get index for self.datalist and key. And then now we simply store the key value pair inside it. So we can simply store the key comma value inside self.datalist idx. Then for list all, again straightforward, self.if kv is not none. So get all the key value pairs that are not empty, and then we simply get kv0 is going to give us the key from kv. So that there it is. Here you can see already that we are creating a basic hash table of max size 1024. So the first thing that we can verify is that the length of the basic of the data list is 1024. There you go. Then you insert some values here. So we insert the value Akash, we insert the key value pairs. So we insert the value 9999 for Akash. So this is one key value pair. We are inserting Hemant and 8888. And what this will do is when you call basic table.insert, it will call this insert function, and self will now point to the basic table that we have just created, because we're calling insert on that specific basic table. So self will point to the basic table. So self.datalist will become basic table.datalist, and then the remaining arguments Akash and 9999 will get passed in as the key and the value. So this code will execute. We will get the index within self.datalist for the key Akash, and then within self.datalist or basic table.datalist in this case, at the given index that we just computed, we will store the key value pair, which is Akash and the phone number. And that's how it will work. So we're inserting some values and then we're finding a value. So once we insert the two values and then we find a value, that should give us the value 8888. You may want to then maybe modify this test case to also include the test for the other value that we inserted. So feel free to modify the test cases or add new test cases so that we're checking not just one value but both the values. Next, let's see how if we can update a value. So we call basic table.update and we set 7777. Now suppose you're not implemented update here. Let's for a moment return. Suppose you're not implemented update here. Then if you called update, you would get false here because the value did not get updated. And you can check that by simply checking basic table.find Akash. You can see that it still has the value 9999. That's how test cases are helpful. Let's remove the return. Okay, so now the value seems to have been updated just fine. Then let's get a list of all the keys, and the list of keys should match true. Once again, if we did not have this kv is not none, then we would get back not just this key value pair, but we would get back all the nuns, and we don't want that. So these were some test cases, but you need to now create more test cases and test them out to make sure that your implementation is correct. Now, once you've done that, you would want to run jovian.commit. Now the next step and this is something that you may have thought about while working through the assignment, is that how do you ensure that different keys do not point to the same index? Because we're doing all these things where we're converting each character into a number and then adding up the characters. Now, obviously, if you have words which have the same characters but in different orders, now obviously there are different keys, but they have the same hash. Listen and silent have exactly the same keys, exactly the same hash. So for instance, you can check get index listen and get index silent. Okay, we also need a data list. Let's put in a data list here. Both of them have the hash 655. That means if you insert a value with the key listen and then you insert a value with the key silent, the data at this position will get overwritten. So when you try basic table.find listen, you will get the value associated with silent, and that's bad. And this is called collisions. This is called a collision because here the two keys are colliding in some sense because they're leading to the same hash. And any hash table that you implement is ultimately going to have collisions because the number of strings or the number of keys is possibly infinite, but you have a limited number of positions or indices in your table. So our hash table implementation is incomplete because there can be data loss and it does not handle collisions. And there are multiple techniques to handle collisions. And the technique we will use in this assignment is called linear probing. And here's how it works. While inserting a new key value pair, if the target index for a key is occupied by another key, then we simply try the next index. And if the next index is also occupied by another key, we try the next, and then we try the next, and then we try the next till we find the closest empty location. And then while finding a key value pair, we apply the same strategy. But instead of searching for an empty location, this time we search for a location which contains the key value pair with the matching key. We get the hash of the key that we want to find, and then we check if that position is occupied by another key, not the same key. Then we try the next index, and then we try the next index, and then we try the next index till we find a position which is occupied by a key value pair for the same key. And if we find an empty position, that means the key does not exist, because if it did exist, then it should have been somewhere in that string of searches that we just did. Now by updating the key value pair, again we apply the same strategy, but instead of searching for an empty location, we look for a location which contains a key value pair with the matching key and update its value. So that's how you handle collisions in a hash table. And to handle collisions, we will define a function called getValidIndex, which first gets the hash using getIndex and then starts searching the data list and returns the first index, which is either empty or contains a key value pair matching the given key. So we are now addressing two requirements in one shot with the getValidIndex function. For insertion, we are looking for an empty position. For find and update, we're looking for a position which is occupied by the given key value pair, okay, or the given key specifically. So here's the getValidIndex function, and I will let you work through this. So you will start with the index returned by getIndex, then while true, because we don't know how long we may need to iterate, get the key value pair stored at the index. This is where you may have to, it's simply a question of putting the index into a data list, getting the key value pair. Now, if the key value pair is none, which means that there is nothing at that index, it is empty. That's great. We're done. We can simply return the index. On the other hand, if it does have values, so then we get the key and value out of it. If the key matches the key that we want to store, great. Then we can return the index once again. If neither of these hold true, we move the index to the next position. But as we move to the next position, it's possible that we may run out of indices, so the index may become equal to the length of the data list. So then we wrap around and go back to the 0th position. So this is an important part where we go around. So now our list is in some sense circular, where we can keep looping around it, so that if we have something that needs to be stored at the last position, but the last position is occupied, then we move back to the 0th position and so on. And then you can check if getValidIndex was defined correctly. And if it was, then these cells should output true. Once again, these are just some sample test cases, so you should include some more of your own test cases here. And then finally, once you're done, just save your work. Now the next step is to incorporate linear probing into your hash table. So here's a new class called probing hash table. Here you need to use not get index but get valid index. It has pretty similar code, so I'll let you work this out. Be aware not to simply copy paste code, and you will run into issues if you copy paste code. So always make sure that you are writing the code yourself and carefully writing each word or each variable and each method and each argument of the code. Then there are some test cases here for you to test the probing hash table. Once again, you can try it out with some examples and see if it works fine. Specifically here, we are taking the same example, listen and silent, both of which in basic hash table would have the same key, but in probing hash table will have the same position, but in probing hash table will have different positions. And that's it. At this point, you're done with the assignment, so you can make a submission. If you have run jovian.commit, you can take this link and make a submission on the assignment page. Or the other option for you is to simply run jovian.submit Python DSA assignment 2. And once you make a submission, it will be evaluated automatically. So let's click through here. So it will be evaluated automatically. And if you scroll down here, you will see that you will get a grade, and not just grade, but you will also get comments for each question. So if you see here, there are question numbers here. You can see that there's question 5, question 4, and so on. So it seems like since we implemented the get index function, since we implemented the data list correctly, question 1 was a pass. Let's see what question 1 was very quickly. Question 1, create a Python list of size max table hash size. Question 2 was a pass. So question 2 was the get index function. Question 3 was a pass. So question 3 was complete the hash table implementation. Question 4 was a fail, get valid index, we've not defined it yet. And question 5 led to an exception, obviously because we have some code which will not execute because we have some blanks that need to be filled in. So keep that, use this as feedback. You will know exactly what to fix. And if you are stuck at any point, you know what to do. You can go to the forum. So let's see the forum here. So this is the forum subcategory for assignment 2. You can create a new topic here if you want to have a longer discussion, or you can simply go to the main topic, assignment 2, hash tables and Python dictionaries. And you can ask a question here. There are already a lot of discussions going on here. So it's possible that your question may already have been answered. And after this, there are also some optional questions. Now here, the optional question is for you to implement a Python friendly interface for the hash table. So instead of defining functions insert, update, and find, you will define the functions get item, set item, and instead of list all, you will define the function iter. And also, instead of using the hash function, instead of using the custom hash function that we have defined, you will use a function that's inbuilt into Python called hash, and it takes any string or any object and it returns a number for it. Now, since hash does not accept a list, so you will have to take the remainder manually. So in this case, for example, we've taken the remainder and gotten back the number 3569. So you define a hash table here. And once you have done that, you will be able to use it just like a Python dictionary. You will be able to use it exactly like this. You create a hash table, and then to insert a value, you use the indexing notation and insert a value. To retrieve a value, you use the indexing notation to get the value back. And here you can compare it with the number. To update a value, you simply use the indexing notation again. And to get a list of values, you simply call the list function, or you can also use it within a for loop. And we've also defined a function called repr and str. What that will do is that will let Python print a representation like this when you simply run a cell which just contains the name of this variable. That's one. And then there are a bunch of improvements that you can try to hash tables. This is a great exercise if you want to improve your Python programming skills and also understand how hash tables work. If you can complete these 4 exercises, there's pretty much no question related to hash tables that you cannot answer. You will know everything about them, and each of these exercises may take another 30 minutes to 45 minutes, but it's completely worth the time. Maybe set aside a few hours on the weekend to work on these optional exercises. Now here's one: how to track the size of the hash table. Instead of having to loop through the entire table to get the number of key value pairs, can you store the length somewhere so that you can track it in size order 1? Here's one: to implement deletion. So to implement deletion, you have a technique called tombstones that are used. So you can use this tombstone technique and implement it. Just a little more code. Can you implement dynamic resizing? So instead of starting out with a hash table of a given size or requiring the user to specify a size, can you maybe start with a hash table of, let's say, 128 elements and then double it as soon as you reach 128 elements, or maybe even before. To avoid collisions, you may want to double it as soon as you reach 64 elements, like 50% of the capacity. So dynamic resizing is the technique that allows you to automatically grow and shrink the data list internally. And then here's another technique for collision resolution. This is called separate chaining. So instead of going to the next index, what you do is you maintain a linked list at each position. And for all the keys, you still use that position, but you look through the linked list while looking for a key, or you add a new element to the linked list for that position if you're adding a new key there. So here's separate chaining explained in a YouTube video. You can look through that and try to explain it on your own. And one final thing here is also the complexity analysis. And here's where you talk about average case time complexity, because on average, if you have a good hashing function and you've implemented some improvements like dynamic resizing, then the average time complexity for insert, update, find, and delete are order 1, and list of course is still order n. On the other hand, the worst case time complexity, because there can be collisions, are still order n. So here's something for you to ponder upon. What is average case complexity and how does it differ from worst case complexity? This is also something that is discussed in lesson 3 of the course, where we talk about quicksort. And you see why insert, find, and update have an average case complexity of order 1 and a worst case complexity of order n. If not, this is something that you can look up online. Try to see if you can search a tutorial and learn why this happens. Then how is the complexity of hash tables different from that of binary search trees? We've discussed binary search trees in a lot of detail in lesson 2. So now the question becomes, when should you prefer using hash tables and when should you prefer using binary search trees or vice versa? So all these very interesting questions, and you may get asked some of these questions in interviews as well. It will help you, especially to ponder upon some of these questions, even if you do not end up solving all of these optional questions. Do look at the complexity analysis and think about it. And there's a forum thread where you can discuss your thoughts. So what do you do next? Review the lecture video, review the assignment walkthrough video, and execute the Jupyter notebook. Complete the assignment and attempt the optional questions as well. And do participate in forum discussions. So this was a walkthrough of assignment 2 of data structures and algorithms in Python. Hello and welcome to Data Structures and Algorithms in Python. This is an online certification course conducted by Jovian. And today we're on lesson 3. My name is Akash. I'm the CEO of Jovian and I'm your instructor for the course. If you follow along with this course and complete 4 weekly assignments and a course project, you can earn a certificate of accomplishment for this course. So let's get started. The first thing we'll do is visit the course website, pythondsa.com. So when you visit pythondsa.com, this will bring you to the course website. Here you can find all the information and material for the course. You can check out lessons 1 and 2 and assignments 1 and 2, both of which are still open for submission. And let's open up lesson 3. So the topic today is sorting algorithms and divide and conquer. And you can watch a video recording of the lesson here. You can also catch a version in Hindi. Now the code used for the lesson is provided here. So let's open up this link, sorting and divide and conquer. This is where all the code is present. So here we have it. Now we are looking at the tutorial and the code for this lesson. If you scroll down, you can see that there is some code here. Now to execute this code, you have two options. You can either execute this code online using free online resources, which is what we recommend, or you can download it and run it on your computer locally. And the instructions for both of these are given here. We are going to use the first one, which is to click the run button at the top of this page and select run on Binder. So let us scroll up here and let us click the run button and then click run on Binder. Now, once you do this, it will open up an interface like this. And what you're looking at here is a Jupyter Notebook. So a Jupyter Notebook is an interactive programming environment where you can write code, look at the results, and you can also write explanations. And we've provided you with a cloud-based Jupyter Notebook setup, so you don't have to install anything. All the code that you execute here will be running on our cloud, but you can also download it and run it on your own computer by following the instructions. So the first thing we'll do is click on the kernel menu and click Restart and Clear Output to remove any of the outputs from previous executions of the code, so that we can execute the code and see the outputs fresh for ourselves. Now I'm also going to zoom in a little bit here so we can look at the code. And let's get started. So this is a coding focused and practical course. And we're talking about different data structures and algorithms. The topic today is sorting algorithms and divide and conquer algorithms in Python. So in every lecture, we focus on a specific problem. So in this notebook, in this tutorial, we will focus on this problem which you're looking at here. So let's read the question. You're working on a new feature on Jovian called Top Notebooks of the Week. Write a function to sort a list of notebooks in decreasing order of likes. Keep in mind that up to millions of notebooks can be created every week, so your function needs to be as efficient as possible. That is the key point here. Now, this is a classical problem in computing, the problem of sorting a list of objects, and it comes up over and over in computer science and software development. And it's important to understand common approaches for sorting, how they work, what the trade-offs are between them, and how to use them. So before we solve this problem, we'll solve a simplified version of the problem. It's quite simple to state. Write a program to sort a list of numbers. And sorting usually refers to sorting in ascending order unless specified otherwise. So that's our question for today. Write a program to sort a list of numbers, and we'll expand upon it to answer this original question as well. Now, this is the method that we've been following throughout the course, and we will continue to follow a systematic strategy for solving programming problems. Step 1, state the problem clearly. Identify the input and output formats. Step 2, come up with some example inputs and outputs and try to cover all the edge cases. And step 3, come up with a correct solution for the problem stated in plain English. Step 4, implement the solution and test it using example inputs. So this is very important that you implement the simple solution. So you just need a correct solution first, not the efficient one, and then you implement it and test it. Then you analyze its complexity, identify inefficiencies, and then you apply the right techniques to overcome the inefficiency. And that is where the knowledge of the right data structures and algorithms comes into picture. And once you apply the new technique, then you once again state the solution, implement it, and analyze its complexity and repeat if necessary. So this is the strategy we'll follow here today as well. So step 1, state the problem clearly and identify input and output formats. Now the problem is stated clearly enough for us. We need to write a function to sort a list of numbers in ascending or increasing order. Now here's the input. The input is a single argument called nums, and that is a list of numbers. So for instance, here's a list of numbers. You can see that they're not in any specific order. And then the output is the sorted version of the input. So here is the same list of numbers in sorted order. And based on these two, we can now write a signature of our function. So our function will be called sort or something else, but it will accept just one input. And right now we've not written any code here, so we just put in pass. Now I'm running this code here using the shift plus enter shortcut, but you can also use the run button on the toolbar. So either run or shift plus enter. And the great thing about Jupyter Notebooks is that you can add more code cells anywhere and test anything that you want. For instance, if you want to insert a code cell below, just click the insert cell below menu option, or click outside a cell on the left and press the B button. And now you can write some code here and run it. So please feel free to experiment with this notebook as you go along. So step 2, come up with some example inputs and outputs. Now, this is very important. You need to think about all the different scenarios in which you may want to test out your function before you put it into production so that you catch errors early on. And thinking about scenarios will help you identify what are the special cases you need to handle in code. And it's easier to do it right now than while writing your code, because that may lead to bugs. So here are some scenarios that I was able to come up with, and there may be more. So you can continue and increase this list. So the first one is some list of numbers in random order. So some numbers in any random order, and you can try slightly smaller lists and larger lists and so on. Second is a list that's already sorted. We need to ensure that an already sorted list does not become unsorted. A third is a list that's sorted in descending order. We may want to check that, see if we need to handle that case separately somehow. Then a list containing repeating elements. This is something you may not have thought of, but the question never said that the number should be unique. So there could be repeating elements here. An empty list, interesting input. The output is also an empty list, or a list containing just one element, or a list containing one element repeated many, many times, or even a really long list. This is something that we may want to test because we want our algorithm to be efficient at the very end. So a long list may help us just evaluate the efficiency empirically. So these are the scenarios, and what we now need to do is create some test cases for these scenarios. So test cases involve creating an input and an output. For instance, here is an input, num0, and this could be the list 431, and here's the expected output. So let me call it output 0, and this would be 134. Now this is a good way to create a test case, and you can use it later for testing, but we will put our tests into this particular structure. We'll create a dictionary, and creating a dictionary like this will help us automate the testing of all our test cases with a single helper function. So what we're going to do is for each test case, create a dictionary, and then it'll have two keys. First key is called input and the second key is called output. And in the inputs for each of the arguments that go into the function, and remember there's just one argument here, we will have one key. So we will have the key nums, and the key nums will have the input value for the test case, and the output will simply contain the output returned by the function. So that's how we'll set up our test cases. So that's our test 0, a list of numbers in random order. Then we have test 1. This is also another list of numbers in random order. You can see here, no specific order. Now we have a list that's already sorted, and the output obviously is the same. Now for the random ordered list, the output is the same numbers in sorted order. Now we have a list that's sorted in descending order, and the output is the same list in increasing order. Then we have a list containing repeating elements. You can see that the numbers 1, 2, 6, and 7, and even -12 repeat here. Here we have the empty list. Here we have a list containing just one element, and here we have a list containing one element repeated many, many times. And then the final test case, which was to create a really long list, that's where we can start with a sorted list created using the range function and then shuffle it to create the input. Otherwise, you may spend a lot of time just creating a list and then writing the sorted version of it. That's too much work. So always use a computer, always use helper functions whenever you can, even to create test cases. So we'll use the range function. Now the range function takes either a single number or two numbers. So you can have something like this, range 2 to 10, or just range 10. And if you just look at it this way, it just prints range 0 to 10. Now, if you actually want to see what's in it, there are a couple of ways. You can do list range 10, and that gets converted into a list, or you can use it in a for loop. So you can put for x in range 10, print x. So you can see that it contains the numbers 0 to 9. And that's important, that the range does not include the end element of the range. Okay, so just keep that in mind. Now, what's the difference between a range and a list? A list contains all the 10 numbers together at once, but a range internally simply maintains a counter. So when you use a range in a for loop, it simply starts the counter from 0 and increments it up to starts the counter from the starting value. So if it's 2 to 10, then it starts the counter from 2 and increases it up to the end value -1. So it does not use as much space as a list. It simply uses one single variable internally, and that's why it's more efficient. In any case, right now we need lists. So what we'll do is we will create a list of 10,000 numbers. So 0 to 9,999. That is our in list. And then our out list is also going to be 0 to 9,999. That's our out list. Both of them are sorted. Now what we do is we shuffle the inner list. So we import the random module from Python, and then we call random.shuffle. And we call random.shuffle on in list, and that shuffles the first list, the in list. So now we have that as the input, nums, and then the out list, the sorted list, is the output. Now, once again, we can even check that in list is actually shuffled, maybe by looking at the first 10 elements. You can see here that these are all shuffled numbers. On the other hand, if you check the out list, you can see that these are all in order. So those are our test cases, and it's very important to create good test cases even in interviews. Before you start coding or before you even suggest a solution, you should try and list out your test cases either verbally to an interviewer. In a coding assessment, you may create a block of comments at the top and start listing some test cases at the top, or you can create proper test case dictionaries like this. It takes a few minutes, but it's totally worth it because you can then test your algorithms very easily. And finally, we'll take all our test cases, test 0 to test 8, and put them into a single list called tests. Great, so we've made some good progress so far. Next, let's come up with a simple correct solution and state it in plain English. And coming up with a correct solution is pretty straightforward. We have a list of numbers, so we iterate over the list. Let's grab a list of numbers so that we have something to look at. Here you go. So we have a list of numbers. So we iterate over the list of numbers starting from the left. So we start from the very left, and then we compare each number with the number that follows it. So we compare 99 with 10. And if 99 is greater than 10, then we can say for sure that 99 should appear after 10 in the final sorted array. And the sorted array, by default, it means the increasing order of numbers, right? So that's what we're solving first. So what we can do is we can simply swap 99 and 10, because we know that 10 should appear before 99 and 99 should appear after 10. Now, once we continue the swap, we move to the next position, and then we compare 99 with the next element 9. That turns out to be higher as well. So we swap it, and then we keep going. So we iterate over the list, and for each element, compare the number with the number that follows it. And if the number is greater than the one that follows it, swap the two elements. Now, you do that once, and that alone is probably not enough to compile the entire list, because the entire sorted list, because 99 in this way will end up at the end if you follow the process, but the rest of the list is still not sorted. So we repeat these steps 1, 2, 3. So once again, we start from the left, and then we start comparing 10 with 9 and then 10 with 8 and so on, and keep swapping elements as we go forward. Now, I have a claim here that you will need to repeat the steps 1, 2, 3 at most n-1 times to ensure that the array is sorted. Can you guess why? And here's a hint. After one iteration of the process, the largest number in the list will reach the very end. So that means that each time you're putting one of the largest numbers at the very end. So you need around n steps. So here's an animation showing the same thing. Here we compare 6 and 5, and then we switch them. Then we compare 6 and 3, and we switch them. Then we compare 6 and 1, and we switch them. Now we compare 6 and 8, and we don't switch them because they're in order. Next we compare 8 and 7, and we switch them. Next we compare 8 and 2, and we switch them. And finally we compare 8 and 4, and we switch them. And in this way, the largest number 8 has reached the very end. So now we can freeze its position, and we can start again from the beginning. And you can see that this time the next number 7 will end up here. And then the next time the number 6 will end up here. And then next time the number 5 will end up here, and so on. So in n repetitions of this process of comparison left to right, we will have sorted the array. And this approach is called bubble sort because it causes the smaller elements to bubble to the top or to the beginning. You can see that the numbers 1, 3 slowly bubble up to the top, and it causes the larger numbers like 8 and 7 to sink to the bottom. And you can watch this entire animation to get a full sense of how bubble sort works. What will also really help is if you can take an example on paper and work it out on your own step by step, especially with sorting algorithms. This really helps. Okay, so now we've come up with a correct solution. Let's implement it, and let's test it using an example. Now the implementation itself is also pretty straightforward. So we have the bubble sort function here, def bubble sort. It takes a list of numbers. Now we may not want to modify the list of numbers in place because then our test cases will not be reusable. So just to avoid modifying our test inputs, we're going to create a copy of the list to avoid changing it. And the way to create a copy, simply call the list function with the list as input. So now we are replacing nums with a copy of nums. Now, depending on your particular use case, this may not be necessary. So this is something that you can actually check while you're in a coding assessment or in an interviewer or talking to an interviewer. Just check with them. Do they want an array to be sorted in place, or do they want a new array to be created? If they're okay with sorting it in place, then you probably don't need this, but you may still just want to keep it in because otherwise you may end up modifying some of your test cases unintentionally, and that may lead to problems. It's always good to create a copy of the input rather than modifying it in place. Okay, so then let's come to steps 1, 2, and 3. And then we'll see step 4, which is the outermost step really. So we iterate over the array. So we take I and we check the range len nums minus 1. So if the number of elements in the array is n, and n can be obtained using len nums, then we want to go from indices 0 to n minus 2. So the total number of indices is 0 to n minus 1. But if you go to the n minus 1th or the last element, there is no further element to compare it with. Okay, so keep that in mind, that you only want to run this iteration till your pointer comes to this point, not till the last element. And that is why we check if we put I in the range 0 to len nums minus 1. So the highest value that it can take is len nums minus 2. Next, we compare nums I with nums I plus 1. So we compare the number with the element that comes after it. And if it is greater, so that means these two are out of order. So then we simply swap them. So we set nums I, comma nums I plus 1 equal to nums I plus 1, comma nums I. Now this is a very interesting way of sorting. In C or C++ or Java, you would have to write 3 or 4 steps to swap numbers. But in Python, it's really simple. First you say xy is, let's say we're saying x comma y are 2 comma 3. So you can see they have the values 2 and 3. And then we simply write xy equals yx. So what happens is the value of y gets placed into x and the value of x gets placed into y. So it's a single step for swapping two numbers. There you go. So we swap the two elements, exactly what we are showing here, swapping the two elements. Next, we repeat this. So now we're doing this from left to the penultimate element. And in this way, we have pushed the largest element to the end. Now we need to repeat this process n-1 times, so that each time we are pushing one of the largest elements to the very end. And in n-1 repetitions of these 3 steps, we will end up with a sorted list. And finally, we return the sorted list, and that's it. So let's test it out with an example. And by the way, if some of this doesn't make sense, so a simple way to debug it is to add print statements here. So you can add a print statement and maybe just print this value. So we've used underscore here because we don't actually use this value, but let's say we wanted to use this value, then we can print that this is iteration j, and then inside it you can print that the value of I is I, and you can also print the value of nums I, and you can also print the value of nums I plus 1, and at the very top you can also print nums. Now if you add all of these print statements and then execute your algorithm, now you will be able to see exactly what is happening inside each iteration. So that's a great way to debug your code if you're facing any issues and also understand what the code does. But in any case, we won't need these. So I'm just going to comment these. So let's test it out. So we get from test 0, we get the nums as input, and then we get the output. And we can print the input and the expected output, and then finally calculate the result by passing nums0 into bubble sort, and then printing the actual output, and finally whether the two match. So you can see here now that the input was this unsorted list, and then the expected output was this sorted version, and that's what we got. So in fact, there was a perfect match. And that's it. So we've implemented our first sorting algorithm. It was pretty straightforward, a few lines of code. As an exercise, you can try to implement it once again from your memory. It's, just write it in plain English first and then try to implement it. It's a good coding practice. And we can also evaluate all the test cases that we have. Remember, we had created about 9 test cases. And to help you evaluate the test cases, we've given you a helper function called evaluate test cases, which is part of the Jovian library. So we install the Jovian library here, pip install Jovian, and then from jovian.python.dsa. So Python DSA is the name of the course, and that's also the module where we have helper functions for this course. Import evaluate test cases, and evaluate test cases simply goes over the list of test cases that you have, and it pulls out the inputs and passes them as arguments to the function provided here, which is bubble sort, and then gets the outputs and compares the outputs, and also prints the information with like what was the input, what was the expected output and the actual output, and whether they match. So let's check it out. So you can see here, this was test case 0, and that worked, which we just tested out. Here's a larger list, including some negative numbers. This worked as well. You can see the test result is passed. Then you have another list here. This seems to work fine too. This is already sorted. Here you have one which is sorted in decreasing order. That works. Here you have one with repeating numbers. That works too. The empty list works. The single element works. And this works too. This is the same element repeated over and over. And finally, here is our final test case. This had 10,000 elements, remember? So you can see that this was the expected output and this was the actual output. So we have successfully sorted 10,000 elements. And that's really the power of programming, that without having to look at any of the numbers, we've just written 4 or 5 lines of code and we've sorted 10,000 elements. So all our test cases passed. Although do look here that it took about 15 seconds for the sorting of 10,000 elements. Now, maybe that's not that bad, but we are looking at probably millions of notebooks every week at Jovian. So we want there to be a faster sorting algorithm. Okay, so before we improve the algorithm, we need to understand the algorithm's complexity and identify any inefficiencies. Now the core operation in bubble sort, if you look at the code here once again, is this operation of comparison. So we're comparing a number with the next number and swapping. Now comparison almost always happens and swapping doesn't happen nearly as often. So if you want to find the time complexity and we want an upper bound or the worst case time complexity, we can assume that roughly every comparison also leads to a swap in the worst case. So if we just count the number of comparisons as a function of the input size, the size of the list that was given as an input, that should give us an idea of the time complexity. Okay. So here we can see that there are two loops and the length of each loop is n-1, and inside the inner loop there is a comparison. So the total number of comparisons is n-1 times n-1, which is n-1 square or n square minus 2n plus 1. Now expressing this in the big O notation, which is to get a rough idea of how the number of comparisons or the number of operations in the algorithm grows with time, we can ignore the lower order terms like 2n plus 1. So we can now conclude that the time complexity of bubble sort is order of n square, and this is also known as quadratic complexity. So we can now verify that bubble sort requires order 1 additional space. That this is an exercise for you, but here's a quick hint. You can see that we are not allocating any new lists. We did create a copy of the list, but we didn't have to. So let's not count that. But apart from that, there is no additional space that was required here. We're not allocating any new variables. We are creating this range, but remember I mentioned that a range simply contains a single variable inside it, which it keeps incrementing for a for loop. So we have these two ranges. So maybe we have two variables assigned. So it's constant irrespective of the size of the input. And that's how bubble sort requires order 1 additional space. Now you may be asked about space complexity, and this is where it's a slightly tricky thing, because sometimes, strictly speaking, space complexity also includes the size of the input, because to store n numbers or n elements, you need n spaces in memory. So the space complexity of bubble sort in that sense is order n. And this is something you can check with the interviewer if they're asking you what is the space complexity, and you can ask them if they just want to know what is the additional space required. So the overall space complexity is order n, because we need to store the actual input list somewhere. But on the other hand, the amount of additional space required is order 1, which is a constant factor independent of the size of the list. So that's how bubble sort works. Now analyzing this order n square complexity and keeping in mind that a list of 10,000 numbers takes about 12 seconds. So if n is 10,000 and n square is multiplied by some constant is about 12 seconds, then if you had a list that was of 100,000 elements, so that would be 10n whole square, or 100 times the same amount of time that it would take to sort it. So that means it would take about 20 minutes to sort 100,000 numbers, which is, I would say, is a bit inefficient now. And a list of 1,000,000 numbers would take close to 2 days to be sorted in Python. Now, if you do it in C++, maybe it might be 4 or 5 times faster. But again, the moment you go from 1 million to 10 million, well, that will actually end up taking a year or so. And that's bad. And that is why n square or quadratic complexity is something that we would like to do away with, because it grows very fast. As soon as you hit maybe 10,000 or 100,000 elements, then it starts taking longer than a few seconds or a few minutes or a few days. And at that point, you can no longer use that particular algorithm. So we need to optimize bubble sort, and the inefficiency in bubble sort comes from the fact that we are shifting elements by at most one position at a time. So each time we go through the list, we capture some information about the list, but we are simply moving one element from left to right, so to speak. And each time we are just moving it one at a time by doing swaps. Rather, it would be nice to just place elements directly maybe a few positions ahead. And that's where we will look at some optimized algorithms. Now, another common algorithm that is used is called insertion sort. And here is the code for insertion sort. So you can look through the code for insertion sort here. And here is an example. You can see how it works. And we'll not look into insertion sort in a lot of detail, but roughly this is how you arrange cards in your hand, which is by starting to move cards around so that maybe on the left edge, you have sorted cards. On the right edge, you have the unsorted cards, and you keep moving the new cards into sorted positions. That's how it works. So here's an exercise for you. Go through this function, read the source code, and then describe the algorithm in plain English. Now, reading source code is an essential skill for software development. This is something that you'll have to do in your work, whether you're doing software development or data science, maybe because there are no comments in the code, there is no documentation, or the person who has written the code is not available or has left the company, or this is some open source library. So in all these cases, you will have to read and understand code. So read it and then describe insertion sort, the algorithm in plain English, then look it up online and see if it matches what you've written. And then second is to also determine the time and space complexity of insertion sort and see if it is any better than bubble sort and explain why or why not. So these are a couple of exercises for you. So that's bubble sort and insertion sort. Now, before we continue, I just want to recall you that this is a Jupyter notebook running on an online platform, hub.binder.jovian.ml. And since this is free, it will shut down after some time. So you want to capture snapshot of your work at regular intervals. And that's where you can use the Jovian library. So you install the Jovian library using pip install Jovian, import Jovian, and then run jovian.commit. Now, when you run jovian.commit, it captures a snapshot of this Jupyter notebook and puts it on your Jovian profile. So now this will be your profile when you run jovian.commit, and you will be able to resume your work by clicking the run button on this page anytime. And this notebook will go to your profile. So you can just click on your Jovian profile or just click home here. And if you check either the overview or the notebooks tab, you should be able to find your notebook here. Like here you go. Okay, coming back now. We're at step 6, where we want to apply the right technique to overcome the inefficiency in the algorithm. Now, to perform sorting more efficiently, we will apply a strategy called divide and conquer. And divide and conquer is a very common strategy used across the board for many different kinds of algorithms. And it has this general steps that is applied in different ways across different problems. So step 1 is to divide the inputs into two roughly equal parts. Okay, they don't have to be exactly equal, but two roughly equal parts. And the idea here is that those two parts can themselves be used as inputs, as sub-problems. So then we use recursion. So we recursively solve the problem individually for each of the two parts. So here you have a problem, you've created two sub-problems out of it, and then you call recursion. So the recursive solution itself will use divide and conquer, and then we'll keep going and so on. But once it gives you the solution, combine the results to solve the problem for the original inputs. Okay, so you have now results of the sub-problems and you combine them and you get back the final result. And then the only last thing you need to know is, because you're going to keep doing this division recursively. So if you have an input of size 100, you will call the same function on inputs of size 50 and 50. Then you will call the same function for each of those 50. You'll call the same function on inputs of size 25 and 25. So each half. And as you keep going, you will eventually end up with small or indivisible inputs. And that is where you can solve the problem directly and include terminating conditions. So that's where the recursion stops. Okay, so you include terminating conditions for small or indivisible inputs. So that's divide and conquer. You take the problem, divide it into two sub-problems, recursively solve the sub-problems, get the solutions of the sub-problems, and then combine them. So you can also call it divide, conquer, combine in some sense. And merge sort is the algorithm that is the classic application of divide and conquer to the sorting problem. So let's take a look at merge sort by looking at an example visually. So here we have a list that needs to be sorted. in increasing order. So remember, step 1, divide the problem into 2 sub-problems. So here we have half the list, a little more than half. Here we have another half. So we have split it into 4 elements and 3 elements. Then we call recursively, we call the same sorting problem, the same algorithm on these two. So we split 38 and 27 into one half and 43 and 3 into another. Here 982 becomes one half and 10 becomes the other. Again, we can split 38 and 27. We can split 43 and 3, 982, 10. So now we've ended up with single elements. So with recursion, we've ended up at this terminating condition. We can no longer split the list. So now we start combining the problems. Now, if you're looking to sort a list with just one element, 38, well, that list is already sorted. So you can return that. And 27 is already sorted, the single element. So you return that. Now we have these two sub lists and we need to combine them. Each has one element. So we can simply compare these two elements and we can tell that 27 comes first and 38 comes second. So that's how you combine these two results to get 27, 38. Then similarly with 43, 3, you combine them to get 343 and you get 982 and 10. Next, you can combine these two results. So this is where now the combination is important. Okay, we need to look through and we can probably tell that 3 should come first and then 27 and then 38 and then 43. So we've combined them here. And similarly here we've combined 9, 10 and 82. And then we take the final results, these two final lists, and then we combine them back to get the fully sorted list. Okay. And we'll talk about this combination or what is called the merge operation in a lot more detail soon. But this is roughly the idea here. You keep splitting it into half and then you combine the halves. So let's now state it in plain English. So first, the terminating condition, if the input list is empty or contains just one element, then it is already sorted, return it. If it is not, divide the list of numbers into two roughly equal parts. Then sort each part recursively using the merge sort algorithm. And by the power of recursion, you will get back two sorted lists. Then merge the two sorted lists to get a single sorted list. And this is the key operation here. And this is why it's called a merge sort, because we are always merging sorted lists and making bigger and bigger sorted lists out of them. And the merge operation is something that you may be asked to write in an interview or a coding challenge, apart from the whole merge sort operation itself. So this is something that you can try to explain yourself. So try to think about how the merge operation might work and explain it in your own words. Here is some space for you. But let's jump into the implementation of merge sort then. Now we will implement merge sort assuming that we already have a helper function called merge. And this is a very useful trick where your program may need some complicated piece of logic or some logic which you have not figured out yet. So all you do is assume that you already have the function and use it first and then implement it later. So here's a merge sort algorithm. So now we have the merge sort algorithm and we have numbers here given as an input to merge sort. Now here's the terminating condition. If the length of numbers is less than or equal to 1, which means if the list is empty or has just one element, return the numbers. Then if not, then get the midpoint. So return length of numbers divided by 2. And remember, we're using the double slash here because a single slash would return a decimal and we cannot use a decimal as an index or a position in the list. So that's why we're using the double slash here. So we take the length of numbers divided by 2. So if the size of the list is 10, so we get back 5 here. Then we split the list into two halves. And here's some interesting syntax for you. And let's look into what the syntax actually means. So let's say you have a list. So this is the list we have. And let's say mid has the value. Well, we can check it here. 1, 2, 3, 4, 5, 6. So 6 elements by 2, mid has a value 3. Now let's check x of mid. What does that give us? Well, that gives us 1, 3, 5. Well, actually x of colon mid means x of 0 to mid. And x of 0 to mid means all the elements from position 0 till before the position mid. So that's very important. Once again, it's like a range. So you get the indices at position 0, 1 and 2, not at position 3. Okay, so that gives us these 3 elements. Then let's check the other thing, x of mid colon. Now what this gives you is this gives you the elements starting from the position mid all the way to the end. So you can also write here -1, or we can also write here len of x -1, or we can just skip it and Python will automatically interpret that you want all the elements starting from mid to the end. That is 12, 5 and 1. So positions 3, 4 and 5. And hence to split the list, all we need is to invoke this 135 and 12, 5, 1. We get back 2 parts of the list. So this is a nice thing about Jupyter. Whenever you don't understand a line of code, just create a cell above or below and try out a simple example. So now we have the left half, nums 0 to mid, and then the right half, so nums mid colon. Now here's where the magic happens. We call the function recursively. So we call the merge sort function itself. So we call merge sort on left, and that gives us back a list, a sorted list for the left half called left sorted. And then we call merge sort function right, and that will give us back a sorted list called right sorted. And then we combine the results of the 2 halves by calling the merge operation. So we are now saying that we want to merge left sorted and right sorted to get back the final sorted numbers, and then we return the sorted numbers. So that's merge sort. So yeah, it's almost seems like magic, but it's pretty small, pretty straightforward. Only about 4 or 5 lines of code if you combine some of these lines. So then let's come to the merge operation, because that seems to be the meat here, right? This is the only missing piece. So to merge 2 sorted arrays, what we can do is we can repeatedly compare the 2 least elements of each array and copy over the smaller one into a new array. So here's what that process might look like. Let's say you have these 2 parts, 147 and 023, and we want to get this sorted list. And notice that these are both already sorted because these are the results of the recursive calls to merge sort. So we keep a pointer on the left on each one. So here we have the pointer at 1, here we have the pointer at 0. We compare the 2. We take the smaller one and put it in the list. How do we know we can put it? Because if this is smaller than this, all these numbers are also greater than 0. And then since 1 is greater than 0 and all these numbers are greater than 1, so that follows that all the other numbers to the right of 1 and to the right of 0 are greater than 0, and hence 0 should come in the first position. So we put it there and advance the pointer. Now you can see here, now we can compare 1 and 2, and this time 1 is smaller. And you know that all the numbers here are greater than 2, so they're also greater than 1. And then all the numbers here are also greater than 1. Hence, we know that 1 is now the next largest number, so we can now put in 1 and advance the pointer and keep going. This time now you compare 2 and 4, so now you can put in 2 and advance the pointer. Now you put in 3 and then advance the pointer. And at some point you will exhaust one of the lists. And when you exhaust one of the lists, then you can stop comparing and you can simply copy over the remaining elements. So we can now copy over 4 and 7, and we've exhausted this list, and we get back the sorted merged array 0, 1, 2, 3, 4, 7. So it's really simple. It involves, each step involves one comparison and incrementing one pointer. So you're either incrementing this pointer or you're incrementing this pointer. Okay. So let's now define the merge operation. And you can see the benefit now of assuming that the function already existed. Now we do not have to worry about the actual sorting and recursion, etc. We simply have to worry about merging 2 sorted arrays. So first we'll create a list to store the results, and we have nums1 and nums2, the 2 left and right lists that we are going to combine. Then we are going to set up 2 indices or 2 numbers for iteration, the 2 pointers on the 2 lists. And we set up each of them at position 0. So each of them are currently at position 0 here. And we loop over the 2 lists. So we say while I less than len of nums1 and while j less than len of nums2. So if you have 4 elements in the left list, then I can go from 0 to 3, all 4 positions. And if you have 5 elements in the right list, j can go from 0 to 4, all 5 positions. Then we check and we remember we want to make sure that both of these indices are valid. If any of those have reached the end, then you want to skip and we can simply copy over the remaining list, right? So as you see here, as soon as we reach this point, there's no more comparisons to be made. So we can exit the loop. So now we check which one is smaller. So if nums1i, so the left list current element is smaller than nums2j, then we append to the merged list nums1i as we did here, and we increment I. So this is exactly what we've done here. So we put in, well, let's say here, so we put in 1 here and we increment the left pointer. On the other hand, if that's not true, we append the element from the right, so nums2j, and we increment the right pointer. So in each case, in each while loop, we are incrementing one of the pointers. And then when the while loop ends, one of the lists would have been exhausted. That's when the while loop ends. So we can get the remaining parts of both the lists. So we can get nums1i colon will get the remaining elements from the first list, the left list. nums2j colon will get the remaining elements from the right list. But remember, since one of them is exhausted, so one of these two is going to be empty, right? Now we can check which one is empty and simply add the remaining one. But here's a simpler solution. We just add both of them to the merged array. So we append both the lists at the end, and this automatically takes care of the empty case. If the left side becomes empty, then this adds nothing to the merged array, and this adds the remaining numbers from the right side. If the right side becomes empty, then this adds the remaining numbers from the left side, and this adds nothing. So that's a small trick. So that's the merge operation. Again, not very difficult. If you have any questions, take this out into specific cells and try it out with examples, and you should see it working. So let's try out the merge operation now. So here we have two sorted lists. You can see here. And there you go. You can see that this is now arranged. All these numbers are now arranged in a sorted order. So now we have the merge operation and we have the merge sort operation. So we can now test out the merge sort function. So we get the first set of inputs and outputs from test 0. And you can see here that this is the input and this was the expected output and this was the actual output as well. Now let's test all the cases using the evaluate test cases function from Jovian. So here we're simply going to call evaluate test cases on the entire list of test cases. And you can see all the test cases seem to be passing. Now, if one of these test cases had failed, what you should do is you should go back and add some print statements inside your merge function or add some print statements inside your merge sort function. The right places to add the print statements is right after the function definition, right after in the body of the function, it can be the first statement and then inside each loop. So inside each loop, whatever are the changing parameters, you should print them inside a loop. And then finally, you can also print the return value of the function. So in this way, you can build a full picture of what your function is doing. And that makes it much easier to solve issues. So test cases and print functions make it easy to fix errors in code. And don't worry if there are errors, there are always errors in code. What's important is you should be able to find a way to fix them easily. And without test cases or without printing, you may get stuck and you may just keep staring at the code and trying to figure out what exactly went wrong. So please do that. Now, one last thing I want you to notice is here the execution took only about 50 milliseconds. On the other hand, remember bubble sort took about 15 seconds. To sort 10,000 numbers. So that's merge sort is much faster, right? A millisecond is 0.0001, 10 to the power minus 3 seconds. So in a second, you can probably sort 200 lists of size 10,000. And that's what makes merge sort so much more powerful, and because it is so much more efficient. And as we analyze the complexity, you will learn that merge sort is in fact more efficient in terms of the big O notation as well. So let's analyze the algorithm's complexity and identify if there are any inefficiencies. Now, analyzing recursive algorithms can get tricky, and that's where it helps to track and follow the chain of recursive calls. So what we'll do is we will add some print statements to our merge sort function and our merge function. So we'll simply see what the merge sort function was invoked with. Okay, so we'll add a print statement inside merge, and we'll add a print statement inside merge sort, both of them. And we're also tracking something called a depth to track the chain or the depth of each recursive call. And you'll see what I mean in just a second. Okay, so this is what it looks like. We called merge sort on this big list of elements unsorted, and that merge sort internally led to two calls of merge sort. So you can see this one here and this one here. So you have two calls to merge sort, one with the left half of the list and one with the right half of the list, and they're unequal. And these two merge sorts finally returned merged lists, and we finally called a merge operation on the two of them. You can see that this is the merge operation, the final merge operation called here on the two merge sort lists. And this merge operation is working with these two sorted lists. Okay. So we can see that each merge sort itself invokes merge sort twice, but this time with an array of half the size. You can see merge sort was invoked with arrays of or lists of half the size. And it also invokes the merge function once to merge the two resulting arrays, the two sorted arrays. Now the two calls to merge sort, if you observe closely, they themselves make two more calls to merge sort and one more call to merge. And then those internal calls make two more calls to merge sort and one more call to merge, and so on, till we end up with single elements, at which point merge sort simply returns that single element. So the merge sort algorithm ultimately boils down to a series of merge operations. You can see here that each merge sort, all it's doing is calling merge sort internally and then calling a merge operation. So ultimately what we are doing is we are first merging 5 and minus 12, and then we are merging 2 and 6, and then we are merging minus 12, 5 and 2, 6, and then we are merging 123, and we are merging 7 minus 12, and then we are merging 7 minus 12, 7, and finally we are merging 123 minus 12, 7, 7, and then finally we are merging the big list, right? So it's ultimately just a whole bunch of merge operations. And if you look inside the merge operation, this is where a comparison is happening, and this is where this append step is happening. So we are comparing and appending. So those are the two key operations here. And with every comparison, there is an append. So if we simply count the comparisons once again, that's happening, that should be enough to get the time complexity. And what is the number of comparisons that's happening? Well, that's straightforward too. If you have two lists, nums1 and nums2, each, and the total length of the two lists is n. So because the number of iterations is equal to, in the worst case, it would be equal to the lengths of the two lists combined. So you may have to first maybe increment I by 1, then increment j by 1, then once again increment I by 1 and j by 1. So the total number of iterations here is len of nums1 plus len of nums2, right? But remember, the merge was called, if merge sort was called with a list of size n, then merge was called with a list of size n by 2 and n by 2 roughly. So the total list, the total length of nums1 plus nums2 is actually the overall length n. So that's the real trick here, that the merge operation is an order n operation where n is the number of elements, the total number of elements. Okay, so this merge operation takes 4 plus 5, 9 comparisons, and this merge operation takes 5 comparisons, and this merge operation takes 3 comparisons, and so on. Now this way, now if we visualize the problem now as a tree where we are calling merge sort with n elements, and that ends up calling merge sort with n by 2 elements, and that ends up calling merge sort with n by 4 elements, all the way down, and then we start merging. So here, when we get to individual elements, we are calling merge with literally single elements. And as we come up here, we are calling merge. At this point, we are calling merge with elements of size n by 8 and n by 8, but we are calling merge 8 times. So each of these subproblems makes a call to merge, and each of these subproblems has the list size n by 8. So you have 8 calls to merge of size n by 8. So the total number of comparisons done is n. And at every stage you can check this. At the top level, you are calling merge with n total elements. So the total number of comparisons is n. At the second level, you're calling merge here once with n by 2 elements, and you're calling merge here once with n by 2 elements. So the total number of comparisons is 2 times n by 2, that's n. And here you're calling merge with n by 4 elements 4 times, so that's n. So if the height of the tree is h, then the total number of comparisons is n times h, right? So on each level, you require n comparisons for the merge, and you call merges at every level for each of these subproblems. So the height of the tree is, so the total number of comparisons is n times h. Now, how do we get the height of the tree? If the height of the tree is h, and you can see here that as we go down, this is level 0 and it has one element. This is level 1 and it has 2 elements. This is level 2 and it has 4 subproblems, and this is level 3 and it has 8 subproblems. So level k has 2 to the power k subproblems. So if you keep going down, this is level h minus 1. So level h minus 1 should have 2 to the h minus 1 subproblems. But remember, at the last level, we simply have subproblems or merge calls with single elements. So that means we have a total of n elements here, or n leaf nodes here. So it follows that 2 to the power of h minus 1 is n. Okay. So I'll let you think about that and reason with that. Now, this is something that you may have to work out on pen and paper to get correctly, that if the height of the tree is h, then 2 to the power h minus 1 is equal to n, because at the bottommost layer you have n leaves in the tree. So it follows that h is log n plus 1. So since we said that there are n times h comparisons and h is log n plus 1, so it follows that the complexity of merge sort is n log n. And that's a big improvement from n square. It may not seem like much, but it is. So n square for 10,000 is 10,000 times 10,000, but n log n for 10,000 is 10,000 times 12 or 13 log to the base 2. So that's about a few hundred times faster. Now, even for an array of 1,000,000 elements, it will only take a few seconds to be sorted. And you can verify this by actually creating a list of 1,000,000 elements. Okay. So the complexity of merge sort is n log n, and you get it by drawing this subproblem tree and realizing that you get a subproblem tree of height log n or log n plus 1. And at each step, you perform a merge operation or multiple merge operations totaling to n comparisons. So n times log n is the complexity of merge sort. Now here's also a discussion about space complexity, and this is something that I will leave as an exercise for you. So do read through this and see if you can reason why the space complexity of merge sort is order n. Okay, so time complexity is order n log n and the space complexity is order n. But here's a hint why it's order n. You can see that inside the merge operation, we are creating a new list, and then we are copying over elements from each of the two lists into the new lists. So we are allocating a new list inside merge. And now now that's no longer constant. That list will have the same size as the size of the problem itself. And hence roughly, that's why the space complexity is order n. Okay. So with that, we conclude our discussion of merge sort. It's a divide and conquer algorithm. You split the list into half, recursively sort both of them, then merge the two sorted lists. And the initial condition is 1 or 0 elements. Now there are several extensions and variations of merge sort called the k-way merge sort, where we split not into 2 parts, but into k parts. Then we have the counting inversions problem, where we modify merge sort a little bit to also find some other information about the list. And finally, we have hybrid algorithms which combine merge sort and insertion sort. So what they do is, for smaller lists, they use insertion sort because that's more efficient. And then for bigger lists, they use merge sort. So as they're splitting the list, when you get to a small enough problem, let's say 10 or less elements, they use insertion sort. And that brings us to our next question, where we make one level of optimization and then we stop. But here we'll go one step further. What we'll do is we will apply another technique to overcome the inefficiency in merge sort. Now, the time complexity is pretty good. You can actually sort millions or even tens of millions of elements with merge sort quite reliably, but it's the space complexity that causes a problem. Now, because merge sort requires allocating additional space, and that additional space is as large as the input itself, that makes it somewhat slow in practice because memory allocation is more expensive than computations. So doing a comparison is very easy. You just tell the CPU to compare two things in the memory, or swapping them is also easy because you're still working with memory that you already have. But when you have to allocate new memory, you often have to then request the operating system to allocate the new memory, and then you have to get its address and do a whole bunch of operations. So it's, let's say, an order of magnitude more expensive than simply doing some computations. So you should try and avoid memory allocations as far as possible. Now, 1 or 2 variables is fine, but if you're dealing with a million elements, so you're probably going to need maybe a few MB of additional space. And that is what may slow down your algorithm a little bit. It would still be n log n, but the constant factor, the cost of each operation will be higher because it involves an allocation. Now, to overcome the inefficiencies, the space inefficiencies of merge sort, we will study another divide and conquer based algorithm, sorting algorithm, and this is called quicksort. And quicksort sorts the array in place, which means it does not create a copy of the array internally for sorting inside each operation, inside each combination operation. So let's see how it works. It's a pretty interesting and pretty smart trick. So here's how it works. If the list is empty or has just one element, return it. It's already sorted. Straightforward. Then pick a random element. If not, pick a random element from the list. Now, this element is called a pivot. Now, there are many strategies for picking a pivot. One is to pick a random element. One is to maybe pick the first element, the last element. What we'll do is we will pick the last element, but you can easily augment our implementation to pick a random element. And then reorder the list. And this is the key operation here. Reorder the list so that all the elements with values less than or equal to the pivot come before the pivot element, while all the elements with values greater than the pivot come after the pivot element. And this element is called partitioning. You're partitioning the array around the pivot. So here's an example. Let's say we take 3 as the pivot element, the final element. Now what we want to do is we want to reorder the elements, and the way we reorder is by doing swapping and comparison in whatever way we can. And that's what we will really focus on, the partitioning algorithm. And you reorder it in such a way that all the numbers to the left of the pivot are smaller than it, and all the numbers to the right of the pivot are larger than it. Now here's the key observation here. Once you do that, you can tell that all these numbers can now be sorted independently, and none of the numbers from here will move to the right of pivot. And similarly, all these numbers can also be sorted independently, and none of the numbers here will move to the left of the pivot. So the pivot is in the correct position in the final sorted array. So it's now in its correct final position, and you can simply call quicksort on this half or less than half, this portion of the array and this portion of the array. And there's no real combination required anymore, right? So because we're doing it all in place, we simply call quicksort on each side of the array. And once this gets sorted and this gets sorted recursively, then you will end up with the entire sorted list, right? And that's how we then continue doing the process recursively. Now on the left half, you once again pick a pivot, and then you arrange the elements around the pivot. On the right half, you once again pick a pivot and arrange the elements around the pivot, and so on and so on, okay? So as I said, the key observation here is that after the partition, the pivot element is at its right place in the sorted array. The two parts of the array can be sorted independently in place. Now, maybe once again, take pen and paper and try to work it out yourself. Again, all of this makes a lot more sense when you actually put it down and solve a real problem, a real example. So here's an implementation of quicksort, and once again, we will assume that we already have a helper function called partition, which can pick a pivot, partition the array, and return the position of the pivot element for the next quicksort step. Okay. So this entire process going from here to here, this is where we'll assume that we have a function and write the quicksort algorithm and then implement the partition function. So here's what quicksort might look like. Now quicksort takes a bunch of numbers, and apart from the numbers, it also takes a start index and an end index. Now, why are we doing this? remember, we want to avoid creating copies of the list. That's the whole thinking here, the line of thinking. So we will call quicksort not with a sublist, which is a copy of a portion, but we will call quicksort simply by passing the same original list, but by changing the start and end index. Okay. Now there is some code here. If end is none, then we are setting end to the length of the list -1. And here's one more thing that we're doing. So the final invocation to quicksort that we'll make will be something like this. We may call quicksort. Let's say there are a few numbers here. So we may call quicksort on a list something like this. And in this case, automatically start will have the value 0 and end will have the value none. Now remember, the quicksort is going to sort the array in place, but we also said that we don't want to modify our test cases. So here's one assumption we are making, that if end is none, which means if quicksort is called just with the list, then we'll create a copy of the list, right? So we'll just create one copy at the very beginning, right when the list is passed for the first time, and then we'll not create any more copies. And you can even skip this line entirely. But the only trouble is that we'll start changing our test case input. So that's why let's keep it and let's keep a copy. But this is only done at the very top level, right? So only when we start, we create a copy so that we're not modifying the input list, but never again. So that's what we're doing here, creating a copy if quicksort was called with a list, and setting end to len nums -1, which is the final valid index in the list. Anyway, putting this aside, this is the real condition here. So if start is less than end, which means, let's say here you have start and here you have end. Now, if start is less than end, that means you have two or more elements, right? If start and end are equal, that means you have just one element. And if start is greater than end, that means you have 0 elements, really. So if start is less than end, that means if you have at least 2 elements, then we call the partition function. We call the partition function on nums, and we say that we want to partition the region start to end. So let's say this is the region start to end. We want to partition it. So we want to pick a pivot and then partition it in such a way that elements to the left of the pivot are smaller than it and elements to the right of the pivot are larger than it. For example, if you want 4 to be the partition element, 4 to be the pivot element, then we will partition the array as 3, 4, 5, 23. So that 3 is smaller than 4 and 5, 23 are bigger than 4. And we will return the position of the pivot element. Okay. So now you partition the array and return the position of the pivot element. So this is the position we get back. And then we can call quicksort on this region and on this region. So we can now call quicksort on start to pivot -1, and we can call quicksort on pivot +1 to end. Okay. So now we are actually explicitly passing in values for start and end. So this will not kick in the next time. So no more copies of the list will be created. So all the recursive calls will keep modifying in place. So even the partition call will modify in place, and we'll see how partition works in just a moment. So partition gets the slice of the original list and it returns the position of the pivot element. Then we call quicksort on the left slice, which is before the partition, the element smaller than the partition. And then we call quicksort on the right slice, which is elements that come after the partition. Okay. Now here is how the partition operation works. It's pretty straightforward too, not that difficult. So what we'll do is we will pick the final element as the pivot element. But if you don't want to pick the final element, you want to pick a randomized element, well, just pick a random position and move that element to the final position. And that's as good as picking the final element now. So random pivot simply involves picking an element, moving it to the final position. But assuming the pivot is in the final position, we then keep 2 pointers, left and right. Now remember, we want to push all the numbers smaller than the pivot to the left, and we want to push all the numbers larger than the pivot to the right. Okay. And what we'll do ultimately is we will arrange them in such a way that some of these are smaller than the pivot and some of these are larger than the pivot, and then we'll move the pivot between them. So we'll see how to do that. So you have the left pointer and the right pointer. Now here's what we do inside partition. while these two pointers are far away from each other, first we check if the element at the left pointer is smaller than the pivot. Well, if the element at the left pointer is smaller than the pivot, which it is, you simply advance the left pointer forward. So this goes to 5. And then we go back to the next loop. Now this time, once again, we check if the element that the left pointer points to is smaller than the pivot. 5 is not smaller than 3, 5 is greater than 3. So if that is the case, then we check if the right pointer is greater than the pivot. Now, if the right pointer is greater than the pivot, that means this number is in its right position. It's greater than the pivot. So we move the right pointer back one space. Okay. So that's the operation we just did. Now, once again, we check, is the left pointer smaller than the pivot? No, it's not. Is the right pointer greater than the pivot? No, it's not. So that means these two numbers are out of place, right? We ideally would want this to be smaller than the pivot and this to be larger than the pivot. So we swap these two elements. So now 0 comes here and 5 comes here. Now, once again, we can check, is 0, the left pointer, smaller than the pivot? Yes. So move the left pointer forward. Then is the left pointer smaller than the pivot? No. 6 is now greater than 3. So we check, is the right pointer larger than the pivot? Yes. So we move the right pointer forward because 5 is still in its correct position. It's on the right edge and everything is greater than 3. So now once again we end up in this position that the left element is larger than the pivot. So we check the right element. The right element is smaller than the pivot. We want it to be larger. So we swap these two because these two are once again out of order. And now you can see that 1, 0, 2 are all smaller than the pivot and 6, 5, 11 are all larger than the pivot. So we do one final check. Is 2 smaller than the pivot? Yes. So we advance the left pointer and now both of the pointers are at the same position. So now we can tell at this point that here, from this point position onwards, all of these numbers are larger than the pivot. So we simply swap this element with the pivot. So there you go. So you end up with 1, 0, 2, 3, 5, 11 and 6. Okay, so that's the partition operation. So again, to understand it yourself, do it on pen and paper, write out this array, create the pivot, create the left pointer, right pointer, and keep creating copies of the array for each step of the loop. Okay, and that's how you understand these things. It's not that difficult. It's just, it involves 2 pointers, so it's a little tricky. Now, this is the code for partition, and I will let you follow this code. We'll go over this briefly, but by this point, since we are halfway into the course now, you should be able to read the code, and then there are also comments here, and understand what we have just discussed in plain English. Understand that in terms of code. Okay, so one exercise for you is to explain this visual approach in plain English step by step, and then the second exercise for you is to read the code and understand it, or maybe even try to write it from memory. So just take the English description and try to write the partition function from your memory. Not memorize the code itself, but convert the English text into code. Okay. So once again here, we have the nums, the